now we are going to discuss the another point, which is suppose if you know f of z, then how to get the f of n by this formula, which is f of n is equal to 1 by 2 by j. We can say the closed counter integral of f of z into z to the power of n minus 1 into dz. So this is the, we can say, when you know f of z, how to get the f of n by this formula. And I've already told you, suppose f of z is in the, we can say, in the ratio of numerator by denominator, then try to convert into partial fractions, and by using the inverse z transform also, you can get back the discrete time domain expression of the f of n. So that is one more method, and this is also one more method. So these two formulas you have to keep in mind. So let me write this formula so that you can easily able to understand. So I've already told you, in the case of continuous time Fourier series, in the case of the continuous time for Fourier transform, what is the formula? As I've already told you, f of omega is equal to integration of t is equal to minus infinity to plus infinity f of t into e to the power of minus j omega t into dt. So this is for the continuous time Fourier transform. Suppose if you want f of t, how to get? It is very simple. I have already told you, 1 by 2 pi integration of omega is equal to minus infinity to plus infinity f of omega into here minus b with a plus j omega t into d omega. So this I have already told you, right? So suppose if you want to write the expression of the Fourier, the Laplace transform, I have already told you f of s is equal to integration of t is equal to minus infinity to plus infinity f of t into e to the power of minus st into dt. I have already told this expression. Suppose if you want f of t from f of s, how to get? I have already told you, this is 2 pi, j you have to keep here, j you have to keep, and here integral from, you can say sigma minus j into sigma plus j into f of s into f of s into e to the power of st into ds. So this formula I have already told you. In the case of the Fourier Laplace transform only, I have already explained this formula in a detail manner. How to remember also I have already told you. So you have to keep an extra factor j. You have to keep some extra factor j, and also you have to in place of j omega, you have to replace j omega by s. So this one, as I have already told you, so therefore, if you remember like this, then everything is going to become very much simple. So this is what I have already told you. So therefore, f of t is equal to 1 by 2 pi j integration of sigma minus j into sigma plus j infinity f of s into the power of st into ds. So this is for the, so these are method for the embedded sketch, so that you can easily able to understand. So this is called, these are the formulas for the continuous time Fourier transform, and these are the formulas for the Laplace transform. So now let's write for the this one. What is the discrete? So discrete Fourier transform, right? So discrete time Fourier transform, I have already told you how to get f of omega. So f of omega is nothing but here sigma replace integration by sigma p plus t by n is equal to minus t to plus infinity f of n into e to the power of so see basically, as I already told you how to do this one. So if you want the discrete time Fourier series, discrete time Fourier transform, replace integration by sigma and replace t by n. So you are going to get minus j omega n. That's it, right? So now if you want the reverse expression, is I already told you f of n is equal to. So see this one don't remember. So this one I'm not telling you how to do this one. So let me rub this part. So now let's go for the here. In this case, I've already told how to get the z transform. So let me write here. So wait a second. There is some type of I can say some type of error is there. So it is not responding. Just wait for 30 seconds. So that things are going to become very much simple. So okay, now let's, in the case of z transform, f of z is equal to simple sigma. See, I have already told you how to remember this one. N is equal to minus into plus infinity f of n. Here I have already told you e to the power of j omega. So So z to the power of minus n, to the power of minus n. How I told is very simple, right? So if you see here, if you see clearly from Laplace transform, if you see what I have did, integration I have replaced by sigma, t I have replaced by n. So here f of n, here e to the power of s is nothing but z I am going to assume. E to the power of s is z, and there is a minus t means minus n. That's it. So this is the, from here we got this term. So from here we got this term, right? I'm already doing it, right? Then if you want the reverse expression, how to write the reverse expression? Let me see here. F of n is equal to, what is the formula? Just now we have discussed it. What is the formula? F of n is equal to, same as it is here. Here replace t by n. That's it. 1 by 2 pi j. Right? So closed contour integral of f of z into z to the power of n minus 1 into dz. So this is a formula. So you see clearly from here, what I did, I replaced t by n here, and this term is same 1 by 2 pi j. Close the counter integral of f of s plus f of z. Here we know already e to the power of s is nothing but z. So you have to keep all the power of n minus 1. You have to keep here. Here t is nothing but n. So you have to keep here minus 1 also, extra factor you have to keep into dz. So these are the changes. So this 1 by 2 pi j is same. Integration, closed counter integration of f of z. E to the power of s is, I already told you, it is nothing but z. So z to the power of. So z to the power of. Here n means t means n, right? So you have to keep some extra number which is minus 1 into dz. So these are the formulas you have to keep in your mind. So these are the formulas always you have to keep in your mind here. So these formulas definitely you have to remember how to get these things. So from Laplace transform only we got the z transform. So I have already told you what is the conversion. E to the power of s, I have assumed it is z. E to the power of s, I have assumed it is z. So we are going to get minus t means minus n, as you can see clearly from here. Then I have already told you what is the Fourier transform. In this domain, f of omega is nothing but f of s inverse of s substitute s is equal to j omega, sigma is equal to 0. Whereas here f of omega is equal to f of j when z is equal to e to the power of j omega, because z is equal to r into e to the power of j omega. So r is equal to 1. So therefore z is equal to 1 into e to the power of j omega. Because you can see because of z, if substitute e to the power of j omega, we are going to get this expression, right? So that is what I am trying to tell you. So these two formulas always you have to keep in your mind. So now the next point is, suppose for f of n, if the z transform is f of z, it is having an ROC1. For h of n, z transform is h of z, and it is having an ROC2. Suppose we are doing the convolution, f of n convolution of h of n, then it will become the product in the either frequency domain, in the Laplace domain, or in the z domain also, which is f of z into h of z. So then what is ROC? See, f of z is defined for ROC1 and h of z is defined for ROC2. If you want both of them to define, then definitely we need to take the common ROC. ROC is nothing but the common ROC of the ROC1 and ROC2, or you can say the intersection of the ROC1 and ROC2. So I already told you the convolution in time domain leads to the product in the frequency domain. Frequency means either it is the Laplace domain or either it is the z domain. So f of 1 is having the Laplace transform. See, f of 1 is having the z transform f of z with an ROC of ROC1, and h of n is having a z transform of h of z with an ROC of ROC2. Then f of n convolution of h of n is z transform is f of z into h of z, and the ROC is the intersection of the ROC of ROC1 and ROC2, the common ROC of the ROC1 and ROC2. So what I am trying to tell you is very simple. See, f of z is defined in ROC1 and h of z is not defined in ROC2. So if you want to basically do the product, then these two should define a common ROC. That ROC is nothing but the intersection of the ROC of ROC1 and ROC2. So finally, you can say that basically the convolution in time domain leads to product in the frequency domain. The frequency can be either Laplace domain or it can be even Z domain also. So f of n has Z transform f of Z with ROC of ROC1, and h of n has the Z transform h of Z with an ROC of ROC2. So f of n convolution of h of n will have Z transform f of Z into h of Z, which is having an ROC, which is the intersection of the ROC of ROC1 and ROC2, because f of Z is defined in ROC1 and f of Z is defined in ROC1 and h of Z is defined in ROC2. So if you want both of them to define, if you want to have these two things to define, an ROC should be the common ROC, or you can say the intersection of the ROC1 and ROC2. The next point is, suppose if f of n is having the same thing, I'm writing in another fashion. So if f of n is having Z transform f of Z and h of n is having the Z transform h of Z, then what is y of n? Then y of n is nothing but f of n convolution of h of n. In the Z transform, y of Z is equal to f of Z into h of Z. And then what is h of Z? H of Z is equal to y of Z by f of Z. So this is called as a transfer function. So what is so same thing, same as the previous case. We have not did anything extra. So this is defined in the ROC1 and this is defined in the ROC2. So what is the ROC of the y of Z? It is nothing but ROC1 intersection of the ROC2. So this is the ROC of the y of Z. And if you want transfer function, which is h of Z is nothing but y of Z by f of Z. What is h of Z? H of Z is the Z transform of the impulse response h of n. So this point always you have to keep in your mind. So finally, I can say only one important thing, which is for f of n, the Z transform is f of Z. It is having an ROC of ROC1, and h of n is having the Z transform of h of Z, which is having an ROC of ROC2. Suppose if y of n is the f of n convolution of h of n, because in the LTI system, the input is f of n and the impulse response h of n, and the output is the convolution of the input and the impulse response. But instead of doing all these crazy things, we can directly do in the Z transform, there's the multiplication. Doing convolution is very hard when compared to multiplication. So always we try to make things simpler. That is the basic agenda of this course. So y of Z is called f of Z into h of Z. As f of Z is defined in the ROC1 and h of Z is defined in the ROC2. If you want both of them to define, then the ROC must be the intersection of the ROC1 and ROC2. So h of Z is equal to y of Z by r f of Z. So this is called a transfer function. What is the meaning of transfer function? Here it is a Z transform of the impulse response h of n. So this point always you have to keep in your mind. So now the next thing is, for f of n, the Z transform is f of Z. And for f of n minus n naught, the Z transform is f of Z into z to the power of minus n naught. So this is a very, very important point always you have to keep in your mind. So let me write here. So let me write this formula so that you can easily able to understand. So let me write this beautiful formula here. Suppose if f of n, so if f of n, so here let me write, if f of n is having the, if f of n is having the Z transform f of Z, then f of n minus n naught, it has the Z transform f of Z into z to the power of minus n naught. So it's a very, very beautiful formula that you always have to keep in your mind. So this formula, as I've already told you, in the case of the Laplace domain also, I've already told you this type of formula only. But let me explain that one also. So let me draw here. So let me write here. So in the case of the Laplace domain, so if f of t has the Laplace transform f of s, then f of t minus a, f of t minus a has the Laplace transform e to the power of minus as into f of s, right? Here, what we have done, in place of t, we have written n. In place of s, we have written z. In place of t, we have written n. In place of, you can write either a also, you can write. You can write like this also. F of n minus a also you can write. So what is the formula? It will be f of z into z to the power of minus a, right? So now, you can see here, s means n is z. So here, if you see, e to the power of s is nothing but z. I have already told you. E to the power of s is nothing but z. So z to the power of minus a. So you don't have to remember all these things. If you know Laplace domain formulas, with the help of logic, you can get back the Z transform formulas also. So for f of t, the Laplace transform is f of s. For f of t minus a, the Laplace transform is e to the power of minus a into f of s. So now same logic apply for this domain. So f of n as j, for f of n as the Z transform f of z, then f of n minus a as the z transform f of z into f of z into here e to the power of s is nothing but z to the power of minus a, to the power of minus a. So this is what I am trying to tell you. So see, z is nothing but e to the power of s. I have already told you so many number of times. So this point always you have to keep in your mind. So z is always equal to e to the power of s, because from the Laplace domain only we have got this relation, right? From Laplace domain only I have told you, from the Laplace domain z is equal to e to the power of s. So e to the power of x is nothing but z to the power of minus a. So this formula always you have to keep in your mind. So now let's see here. So this formula you have to always keep in your mind. So now let's see here. So suppose with the help of this formula, let's apply the concept here. So for x of n, the z transform is x of z. For x of n minus 1, the z transform is z to the power of minus 1 into x of z. For x minus 1 minus x of n minus 1, what is z transform? X of n z transform is, so the separation of these two things. So here also the separation of these two things. Therefore x of z is common. So 1 minus z to the power of minus 1. So if you do the separation of these two things, we also have the separation of these two things, and you take the x of z as common, then we are going to get 1 minus z to the power of minus 1. So this one always you have to keep in your mind. So this one always you have to keep in your mind. So f of n as the transform f of z, then f of n minus n naught as z transform z to the power of minus n naught into f of z. I already told you how to remember also. So now let's go for the another formula. Suppose f of n as the z transform f of z. So for f of n, the z transform is f of z. Then sigma k is equal to minus m to n f of k is nothing but sigma k is equal to minus m to n f of k is nothing but, I can write like this. It is nothing but f of n convolution of u of n. So this we can write like f of n convolution of u of n. You can write like this. Suppose if you ask me how it is like this, then I can prove it also. Let me prove for you. Suppose in case if you have doubt, I can prove this one. So give me a second so that I can prove this one. So give me a second here. So here, what I have told. So what I have told here, I have told you that sigma k is equal to minus m to n f of k. This is something that is equal to f of n convolution of u of n. Why it is like this? Let me tell you. So you know, f of n convolution of u of n. So what is the formula? Sigma k is equal to minus infinity to plus infinity f of k into u of n minus k, right? U of n minus k. So now I want to actually draw the graph of u of n minus k. We are defining with respect to k, right? So with respect to k, so first let me draw the u of n graph. So see, let me draw the u of k graph. So u of k. So what is the u of k? Initial point is 0 and the final point is infinity. So for the u of k, the starting point is 0 and the final position is at infinity. Then for, I already told you, this u of n minus k, you can write like this, right? U of minus k plus m, because here k is the variable. K is the variable. So what is the property I can apply? I can apply the shifting property, right? What is the standard format? U of minus k minus of minus n. So I can write like this, right? The shifting property. So shifting property I can apply. F of t minus n, shifting property. So f of t minus n is, it is nothing but minus n. So we have to add minus n to the initial position as well as the final position. So 0 minus n is minus n. Infinity minus n is nothing but infinity only. So now the initial point has become minus n and the final point has become n. So now again there is a minus. There is a minus means again you have to divide by minus 1 in the initial point as well as the final point. So minus n by minus 1 is nothing but n, and infinity by minus 1 is nothing but minus infinity. So now what is the initial point? So if you draw the graph, how you are going to get final graph? The final graph is like this you are going to get. So this is with respect to k. So this is the overall graph of u of n minus k. So what is the thing? The initial point is n and the final point is at minus infinity. So this is the graph that we are going to get, and its value is equal to 1. And its value is equal to 1. Suppose now if you see for more than n, its value is equal to 0. So u of n minus k is equal to 0 for n, for k greater than n. So therefore, if you do the summation from, so this is going to result to what value? Sigma k is equal to minus infinity to n only, because after that the u of n minus k is equal to 0. So 0 into 20 is again 0. That is the reason it is going to become like this. So always you have to write in the standard format of f of t. When I say always you have to do the shifting and then you have to go for the scaling. Only shifting, then follow the scaling. I've already told you this important point. First, you always go for the shifting, then you have to apply for the scaling. So first you have to go for the shifting and then time scaling. So this one always you have to keep in your mind. First you have to go for time shifting and then you have to go for the time scaling. So always what is the standard format? F of t minus a shifting standard and f of at is a time scaling. This is the things always you have to keep in your mind. So what is the standard format for shifting is f of t minus a, and what is the standard format for time scaling is f of at. So this point I have already told you so many number of times. So that is the reason sigma k is equal to minus m to plus n f of k into u of n minus k is nothing but sigma k is equal to minus m to n f of k. So this is the graph that we are going to get. So this is the graph that we are going to get. So this is what we have told here. So that is the reason this is nothing but f of n combination of u of n. So I have already told you that convolution and time domain we need to product in the z transform. So it will become f of n z transform is f of z and u of n z transform, z by z minus 1. Just now we have discussed that. For u of n, what is the z transform? Z by z minus 1. So do the multiplication of these two things. Then we are going to get f of z by 1 minus z inverse. This is what that we are going to get here. So this is the, we can say, the overall z transform of this signal. So finally I can say for f of n, if the z transform is f of z, then for sigma k is equal to minus m to n f of k, which is nothing but f of n combination of u of n. I can combination and time domain leads to the product in z transform. So f of z into u of z. The z transform of u of n is nothing but z by z minus 1. With the multiplication of these two things, we are going to get f of z by 1 minus z to the power of minus 1. So now let's go for the other important concept. What is the important concept? Which is suppose for f of n, if you apply the z transform, then what you are going to get? F of z is equal to sigma n is equal to minus m to plus infinity f of n into z to the power of minus n. So sigma n is equal to minus m to plus infinity f of n into z to the power of minus n. That is called as a first equation. So that is called as a first equation. And what is the second equation? F of n. For f of n, if you apply z transform f of z, then we are going to get sigma n is equal to 0 to infinity f of n into z to the power of minus n. So this is the second equation. So what is the difference between the first equation and second equation? In the first equation, we are taking n from minus n to plus infinity. Whereas in the second equation, we are taking the value of n from only 0 to infinity. So what is the meaning of this one? Here, we are covering the f of n from minus n to plus infinity in the first equation. Whereas in the case of second equation, we are covering only f of n from only 0 to infinity. So equation 1 is called as a two-sided z transform or bilateral z transform. Whereas second one is called as the one-sided z transform or unilateral z transform. So listen carefully. This is called as the two-sided z transform or the bilateral z transform. Whereas this is called as the one-sided z transform or the unilateral z transform. So this is what I am trying to tell you. So these things always you have to keep in your mind. So in the first case we can say that the from minus m to plus infinity we are going to cover the signal. That is the reason it is called as the two-sided z transform or the bilateral z transform. Whereas the equation 2, here we are going to consider the signal range only from sigma n is equal to 0 to infinity. So because of that reason, we can say this is called as the single-sided or one-sided z transform or the unilateral z transform. So this point always you have to keep in your mind. So there you go. See, until now, whatever the formulas that we have studied, these are all the formulas only for the bilateral z transform or the two-sided z transform. So whatever the formulas that we have studied up to now, all these are going to belong to the two-sided z transform or the bilateral z transform. So this point always you have to keep in your mind. So whatever the concepts that we have learned until now, all these are going to valid for the two-sided z transform or the bilateral z transform, because here we are going to consider signal f of n from minus m to plus infinity. So that is the reason we can say this is basically bilateral z transform or two-sided z transform. Whereas in the equation 2, here we are going to consider the signal only from one-sided, only from n is equal to 0 to infinity, only one side. So that is the reason it is called as the one-sided z transform. So finally, let me write these equations so that you can easily able to understand. So see, listen carefully. In the case of Laplace transform, I will write here f of s is equal to integration of t is equal to minus f2 plus infinity f of t into e to the power of minus st into dt. So this is called as the two-sided. So this is called a two-sided Laplace transform or the bilateral Laplace transform. Whereas f of s is equal to integration of t is equal to 0 to infinity f of t into e to the power of minus st into dt. So this is called as the one-sided Laplace transform or unilateral Laplace transform. Whereas f of z is equal to integration will become summation. T will become n is equal to minus infinity to plus infinity f of n into, I already told you, the power of x is nothing but z. So z to the power of minus n. So this is called as the two-sided z transform or bilateral z transform. Whereas f of z is equal to sigma n is equal to 0 to infinity f of n into z to the power of minus n. So this is called as the usual one-sided z transform or unilateral z transform. So these things always you have to keep in mind. So from Laplace transform only we have got the z transform just by interchanging the integration by summation and t by n, and e to the power of s is nothing but z. So always remember z is equal to e to the power of s. S is nothing but sigma plus j omega. So if you simplify, we are going to get e to the power of sigma into e to the power of j omega. E to the power of sigma, we are going to assume it is r. So r into e to the power of j omega. So in the case of Laplace transform, what is the ROC? The ROC is nothing but real part of s, which is nothing but sigma. In the case of Z transform, the ROC is nothing but which is equal to modulus of the Z, which is nothing but r. R is nothing but e to the power of sigma. So these things always you have to keep in your mind. So this is called as the two-sided Z transform or the bilateral Z transform, and this is called as the one-sided Z transform or the unilateral Z transform. So now, until now what we have done, how these concepts are for the bilateral Z transform. So now we will discuss what will happen if you apply the unilateral Z transform. Then you will see what is going to happen. See, for f of n, if you apply the unilateral Z transform, we are going to get f of z. For f of n minus 1, if you apply the unilateral Z transform, then what is the thing that we are going to get, which is f of z into z to the power of minus 1 plus f of minus 1. F of n minus 2, if you apply the unilateral Z transform, then we are going to get f of z into z to the power of minus 2 plus f of minus 1 into z to the power of minus 1 plus f of minus 2 into z to the power of minus 0. Z to the power of minus 0 is nothing but, basically we can say that it is nothing but simply we can say 1. And f of n minus 3, if you apply the unilateral Z transform, we are going to get f of z into z to the power of minus 3 plus f of minus 1 into z to the power of minus 1 plus f of minus 2 into z to the power of minus 2 plus f of minus 3. So f of minus 3. So this point we have to keep in your mind. Similarly, until here, f of n minus n naught, if you apply the unilateral Z transform, we are going to get f of z into z to the power of minus n naught plus f of minus 1 into z to the power of minus 1 plus f of minus 2 into z to the power of minus 2 plus f of minus 3 into z to the power of minus 3 until f of minus n naught. Until f of minus n naught. Until f of minus n naught. And n naught is basically positive, because n naught is positive that we have discussed, right? So this part you have to remember. So we will tell when n is a positive and n is negative, we will see different formulas. So first let us learn this one. Suppose if the bilateral transform is, these extra factors are not there, only the first term we have to consider. So you can see clearly this is nothing but the bilateral Z transform here. So if you apply the unilateral Z transform, so these extra factors are going to get come. But if you apply the bilateral Z transform, these extra factors won't come. These extra factors, except the first factor, the main factors won't come in the case of bilateral Z transform. But in the case of unilateral Z transform, these are going to get come. So let me write this formula so that you can easily able to understand what I am trying to tell you because these forms are very much important. So I'll discuss one of them in a very detailed manner. So listen carefully. So for f of n, what is the unilateral Z transform, which is f of z. So for f of n minus 1, what is the unilateral Z transform, which is f of z into z to the power of minus 1 plus f of minus 1. Then f of n minus 2. What is the unilateral Z transform? F of z into z to the power of minus 2. Then f of minus 1 into z to the power of minus 1 plus f of minus 2. So if you see clearly, see whatever this number minus 1, if it comes here, stop it. Don't write anything z here. So first f of minus 1, then f of minus 2. So minus 2 got right. So don't write anything. So what I am trying to do is very simple. Take z to the power of minus 1, then z to the power of minus 0. Take z to the power of minus 2, z to the power of minus 1, then z to the power of minus 0. Stop until you get z to the power of minus 0. So after getting z to the power of minus 0, you stop it. So similarly, f of n minus 3. So f of n minus 3 means you can see clearly f of z into z to the power of minus 3. So start from f of minus 1. So f of minus 1 into z to the power of, here 3 means next number 2. So wait a second, just wait a second, let me clarify. So f of z into z to the power of minus 3, f of minus 1, f of minus 1 and f of minus 1 is also z to the power of minus 1 only. Then f of minus 2 means z to the power of minus 2 plus f of minus 3. So a small correction here. Let me rub this part. So let me rub this part. So this is not there. Just wait a minute. Wait a second. So just wait a second. Okay. So listen. F of n means f of z, right? F of n minus 1 means f of z into z to the power of minus 1. Then go from f of minus 1. So if this minus 1 you have got here, right? So stop it. Then f of z into z to the power of minus 2. Then f of minus 1. Then f of minus 2. So minus 2 you got here. So stop it. So here minus 1 is z to the power of minus 1. Right? Now f of z into z to the power of minus 3. Then f of minus 1, f of minus 2, f of minus 3. So write until up to f of minus 3. Here minus 1 means here also minus 1. Here minus 2 means here also minus 2. So don't write anything here. So finally, let me go for f of n minus 4. So now you understand what I am trying to tell you. So f of n minus 4, I will write here. Listen carefully. How do I let me tell you? First write f of z. Then z to the power of minus 4, right? Okay. Then listen. First write f of minus 1. Okay. Leave some gap and write f of minus 2. So leave some gap. Again write f of minus 3. Then write f of minus 4. So write until up to here only, right? Then here z to the power of minus 1, z to the power of minus 2, z to the power of minus 3. That's it. So this is what I am trying to tell you. Suppose finally I will go for f of n minus 5. So I will write finally like this one. So f of z into z to the power of minus 5. So write from f of minus 1. So f of minus 1, leave some gap, f of minus 2. So leave some gap, f of minus 3. So leave some gap, f of minus 4. Leave some gap, and f of minus 4. So minus 5 up to right, minus 5 out to right here. So minus 1 means here also minus 1, minus 2 means here also minus 2. Then minus 3 means here also minus 3. Then minus 4 means here also minus 4. So listen carefully how to, I will give you the shortcut. So f of n means f of z. So here f of n minus 1 means f of z into z to the power of minus 1. So what is the next number? Now to start from f of minus 1. So f of minus 1 you got. So stop it. Then f of n minus 2 means f of z into z to the power of minus 2. Then I already told you how to start from f of minus 1, then f of minus 2. So minus 2 you got. Start it here. Here minus 1 means here also minus 1. Here f of n minus 3 will start from f of z to the power of minus 3 plus then minus 1, f of minus 1, f of minus 2, f of minus 3. So minus 3 will stop. Then remaining things take this power. Minus 1 means here also minus 1. Here minus 2 means here also minus 2. Similarly, f of n minus 4 means f of z to the power of minus 4. Then what is our sequence here? The next thing is f of minus 1, f of minus 2, f of minus 3, f of minus 4. The remaining thing, take the same powers. Z to the power of minus 1, z to the power of minus 2, z to the power of minus 3. Then f of n minus 5. F of n minus 5 means simply, I've already told you how to do this one. F of z into to the power of minus 5 plus go from minus 1, minus 2, minus 3, minus 4, minus 5. So minus 1 means here also minus 1, here minus 2 means here also minus 2, here minus 3 means here also minus 3, here minus 4 means here also minus 4. So this is what I am trying to tell you. So this is what I am trying to tell you. Suppose if you want the general expression, so write the general expression. So how you will write general expression? F of n minus n. So how you will write is very simple. First write f of z into z to the power of minus n. Okay. Now start from f of minus 1. Again f of minus 2. Again f of minus 3. Again f of minus 4. Finally it will be plus f of minus n. Okay. Here minus 1 means here also minus 1. Here minus 2 means here also minus 2. Here minus 3 means here also minus 3. Here minus 4 means here also minus 4. That's it. Up to here. But last one, don't write any power. Take as it is. So this is the formula we have to keep in mind. So I've already told you, only because of the unilateral transform, unilateral transform, these extra parts are going to get come. If you take the bilateral transform, all these extra factors won't come. Only the first terms are going to get come. So this is what I'm trying to tell you. So now the next formula is, suppose here up to now n naught is negative. Suppose if reverse, if I naught is positive, then how to do? I will discuss now. Listen carefully. So now here, see, this formula is applicable for both the things. Here the formula is applicable for both the things. Here, suppose if f of n plus n naught. If f of n plus n naught means what is the formula? F of z into z to the power of plus n naught. So this formula also you have to keep in mind. The ROC is same. The ROC is same. Only we are shifting the signal, right? Only we are shifting the signal, right? So ROC is same. So therefore, you can say this form you have to remember. Here minus means here minus, here plus means here plus. For the bilateral Z transform. So now let's go for this unilateral Z transform. Let's see here. F of n means the unilateral Z transform is f of z. So for f of n plus 1, the unilateral Z transform is z into f of z minus z into f of 0. For f of n plus 2, the unilateral Z transform is z square into f of z minus z square into f of 0 minus z to the power of 1 into f of 1. And f of n plus k, the unilateral Z transform is z to the power of k into f of z minus z to the power of k into sigma n is equal to 0 to k minus 1 into f of n into z to the power of minus n. So we have to how to remember the sequence. Let me tell you how to remember the sequence. Let me tell you in a very detailed manner. I think you have understood this formula, right? So this formula always you have to remember it. You have to remember it. So here minus means here minus, here plus means here plus. In the case of bilateral, only the first terms are going to get. In the case of unilateral, the extra terms are also going to get come. So we will see how it is like this in a detailed manner. So this is for this case. Suppose for f of n, what is the unilateral Z transform? F of z. So for f of n plus 1, so f of n plus 1 is very simple. Z to the power of 1 into f of z. So the next term is minus z into f of 0. F of 0. So f of m plus 2 is nothing but unilateral Z transform is z square into f of z minus z square into f of 0, small f of 0, not capital, small f of 0 minus z into f of 1. So general format, let me tell you, f of n plus k. I want you to remember this general format. F of n plus k, where k is a positive. So unilateral Z transform, what is the thing? Z to the power of k into f of z minus z to the power of k into sigma n is equal to 0 to k minus 1 into f of n into z to the power of minus 1. So a small example, let me take this one. Suppose if k is equal to 2, what is going to happen? We will see by applying this formula. So f of n plus 2. For this, what is the unilateral Z transform? Z to the power of 2 into f of z. Okay, minus to the power of 2 into sigma n is equal to 0 to that k is nothing but 2. 2 minus 1 is 1. So f of n into z to the power of minus n. So we will see, we will simplify this one. What we will see minus z square into well, n is equal to 0 and n is equal to 1. N is equal to 0 means f of 0 into z to the power of minus 0. Z to the power of minus 0 is nothing but 1. 1. Now, next one, f of 1 into z to the power of minus 1. Right? So take this z square inside and find what you are going to get. Z square into f of z minus z square into f of 0. So z square into z to the power of minus 1 is z to the power of 1 only. So minus z to the power of 1 into f of 1. Right? So same thing we have got. So we have got the same form, same thing. Right? So I want you to remember only this one. Let's go for what happens if we substitute n is equal k is equal to 1. So we'll check this k is equal to 1 also, we'll check finally, and you will see whether whatever we are going to get is true or not. Let us check k is equal to 1. If you substitute k is equal to 1, f of let us check k is equal to 1 also. F of m plus 1. So what is the formula? Z to the power of 1 into f of z minus z to the power of 1 into sigma n is equal to 0. K is equal to 1. So 1 minus 1 is nothing but 0. So only one thing we are going to get, which is f of 0 only. So f of 0 into z to the power of minus 0 is nothing but 1. So we don't have to keep these things. So multiply z, we are going to get z into f of z minus z into f of 0. So this is what we are going to get for f of n plus 1. Is it same thing or not? Yes, same thing. So I want you to remember only this formula. This formula only I want you to remember. So now you to remember remaining things. So let me write this last formula so that you can easily able to understand. So and k is equal to positive. So k is equal to positive. I will explain how to write the negative value of f of n minus n naught for unilateral transform. For n naught is equal to positive, I have already told you. But for this one, so for this one, let me write here. So let me write here. So f of n plus k. So f of n plus k. Let me write here. What is the formula? Z to the power of k into f of z minus z to the power of k into sigma n is equal to 0 to k minus 1 into f of n into z to the power of minus n. So this one you have to keep in your mind. Suppose if k is negative. If k is negative means how? Then k is negative. Suppose n minus k. Here k is positive. Here also k is positive. Then how to get this one? I want to discuss this one. We have discussed that. If k is positive means I want to tell you f of z into z to the power of minus k. Then comes the f of minus 1. Then comes the f of minus 2. Then comes the f of minus 3 until you get f of minus k. So here minus 1 means here also minus 1. Here minus 2 means here also minus 2. Here minus 3 means here also minus 3. So like this. So finally, let me write all these formulas. So this last two formulas I will write because these are very, very important. So listen carefully. But k is always positive. So k is always positive. So k is always positive. So these two formulas you have to remember. So let me write one after the another. So f of n minus k. So for this one, what is the unilateral z transform? Let me write here. So f of z into z to the power of minus k. Okay. Then f of minus 1. Here write f of minus 2. Then here f of minus 3. Here finally you are going to get f of minus k. Okay. Here minus 1 means here also minus 1. Here minus 2 means here also minus 2. Here minus 3 means here also minus 3. Like that. But don't write here anything. Suppose f of n plus k. F of n plus k. If you apply unilateral transform, what is the formula? We have to remember z to the power of k into f of z. F of z minus z to the power of k into sigma n is equal to 0 to k minus 1 f of n into z to the power of minus n. That's it. If you remember these two things, then you can solve any of the unilateral z transforms. So k is a positive in both the cases. K is a positive in both the cases. So these things always you have to keep in your mind. So these things always you have to keep in your mind. So these are the formulas always you have to keep in your mind. So in the case of bilateral, these extra factors won't come. only these first terms are going to get come. But in the case of unilateral jet transform, all these extra parts are also going to get come. So these things always you have to keep in mind. Now we are going to discuss the another concept, which is the properties of the ROC. So we are going to discuss all the properties of the ROC. ROC means region of convergence. So for what range of the real part of S and the amount of the Z. For what range of these things, the Laplace transform or the Z transform, they are going to get exist. So all these properties that we are going to discuss regarding the ROC. So we are going to discuss all the properties of the ROC. ROC means region of convergence for the Laplace domain as well as the Z domain. We are going to discuss in very detailed manner. The first point is ROC of the Laplace transform is rectangular strips, whereas the ROC of the Z transform is angular strips. I already told you in the case of the Laplace transform. So here let me write here. In the case of Laplace transform, I already told you the ROC is nothing but the real part of S. The real part of S is nothing but sigma. So sigma. So sigma is nothing but here you take the S plane. So you take the S plane. So this is the S plane. This is the sigma and this is the J omega. Suppose let me assume what is the region of convergence. Let me assume some example. Zeta is greater than 2. So zeta is greater than 2 means, so this is the 2, right? So this is the 2. So then what is the region of convergence? So this is the region of convergence. So for all range of this sigma, the Laplace transform is going to get exist. So therefore we can say this is the basically a strip, is a rectangular strips. So what is the ROC? The ROC is nothing but it is a rectangular strips in the case of the Laplace transform. So in the case of Laplace transform, the ROC is nothing but the rectangular strips. Now let's go for the Z transform. In the case of Z transform, what is the ROC? ROC is nothing but the map of the Z. The map of Z is nothing but it is equal to R. And I've already told you what is the R. R is equal to e to the power of sigma, as I already told you in the previous class only. So what I can do here, so let me draw the Z plane. So let me draw the Z plane. So let me draw the Z plane. So you can see clearly this is a Z plane, right? So this is a Z plane. So Z plane has the magnitude as well as the phase angle. So here let me assume the ROC. Suppose the ROC for some condition R is greater than 2, greater than or equal to 2. Let me case here. So let me take a circle of radius 2. So this is a circle of radius 2. So this is a circle of radius 2. So what is the convergence? It is outside the circle of radius 2. So this is called as the region of convergence. So you can see clearly from this picture. So this is the ROC. So therefore we can say this is nothing but angular strips. So what is ROC here? It is an angular strips. So this is the reason I am trying to tell you that in the case of Laplace transform, the ROC is the rectangular strips, whereas in the case of the Z transform, the ROC is in the format of the angular strips. So therefore we can say the ROC in the case of Laplace transform is a rectangular strips, whereas ROC in the case of Z transform is angular strips. So these point always you have to keep in your mind. So finally I can say the ROC in the case of Laplace transform is rectangular strips, whereas the ROC of the Z transform is basically angular strips. So finally I can say the ROC in the case of Laplace transform is rectangular strips, whereas the ROC in the case of Z transform is a angular strips. So finally I can say the ROC in the case of Laplace transform is a rectangular strips, whereas the ROC in the case of the Z transform is the angular strips. So I explained in a very detailed format also. So these things always you have to keep in your mind. In the case of Laplace transform, the ROC is nothing but the real part of S. So for a certain condition of ROC to sigma greater than or equal to 2, we can say the ROC is nothing but rectangular strips, as you can see clearly here. Suppose in the case of Z transform, the ROC is nothing but the amount of the Z which is equal to R. So R is nothing but e to the power of sigma. Suppose I am going to assume the ROC is R greater than or equal to 2. So I am going to draw a circle of radius 2, and this RGC is outside this circle of radius 2. So I have drawn the picture also. So therefore here the ROC is angular strips. So finally I can say in the case of Laplace transform, the ROC is basically in the format of the rectangular strips, whereas in the case of Z transform, the ROC is in the format of the angular strips. So these things always you have to keep in your mind. So now let's go for the other point, which is if I keep any pole value in f of s, then it won't converge. ROC won't consider pole values, poles always, but ROC is bounded by the poles, but won't consider them. Listen carefully. If I keep any pole value in f of s, then it won't converge. ROC won't consider poles values, poles always. ROC won't consider poles always, but ROC is bounded by the poles, but won't consider them. So what is the meaning of this one? Suppose in the case of the f of s, if you substitute the pole values, then the denominator is equal to 0. So therefore only value will become infinite. It won't converge, it will give some infinite value, or you can say it is undefined. So ROC won't consider pole always, means ROC won't include the poles, but ROC is bounded by the poles, but won't consider them. So what is the meaning of this one? Here let me tell you. Suppose you take the f of s equation, it has numerator and the denominator. Numerator roots are called as the zeros and denominator roots are called as the poles. So if you substitute these poles roots in the f of s, then the denominator is 0 and the numerator is not equal to 0. So all you are going to get infinity, means it is not defined, it is undefined. Instead is going to give infinity, means it is not converging, it is close to infinity. Then ROC means if you keep any value in this ROC, it will give a finite value, but in this case you are going to get infinite. So ROC won't include the pole value. It is always bounded by the poles, but it won't consider the pole values. So ROC won't consider the poles always, but ROC is bounded by the poles, but won't consider them. Means the ROC won't consider the poles. It will only bounded by the poles, but it won't consider them. So this is what I am trying to tell you. So therefore we can say finally in simple words that whenever you keep any pole value in the f of s or in the f of z, the value we are going to get infinite, means it is not going to be a finite value. So we can say it is not at all going to get converged. Then we can say the ROC, whenever you keep any ROC value in the f of s or f of z, you should get a finite value, but here you are going to get infinite value. So therefore the ROC won't consider the poles. ROC won't consider the poles. So ROC is always bounded by the poles, and it won't consider the poles. So ROC won't consider the poles, but it is always bounded by the poles. So this is what I am trying to tell you. The next point is same thing happens in the Z transform, but in this ROC won't consider the amount of the poles. So this is the point always you have to keep in your mind. So here also same thing. In the case of Z transform also same thing. The ROC won't consider the won't include the poles, means the amount of the poles, and the amount of the poles in the case of Z transform. There in the case of the Laplace transform, there the values of the poles, take those values as it is. So let me write here. So we can say that finally, so therefore finally I can say that, see, I have already told you, listen carefully, I am going to explain in a very detailed manner. So in the case of the Laplace transform f of s, the numerator roots are called as the zeros and the denominator roots are called as the poles. So if you substitute these pole values in the f of s, you are going to get infinite, means it is not going to give converge. It is not going to give finite value. It is not converging, means it is not going to give finite value, so it is going to give infinite. So ROC always, whenever you keep any value of ROC in f of s, you should get a finite value. But here, if you keep the pole, it is going to give infinite value. So definitely, ROC is not going to consider the poles, but it is always bounded by the poles. Same thing happens in the case of the Z transform also. But here, in this case, in the case of the Z transform, the ROC won't consider the amount of the poles. Whereas here, the sigma can be positive or negative. The poles can be either positive or negative, but here always take the amount of the poles in this case of the Z transform, because here we are going to ROC is nothing but here the radius. The radius is nothing but the magnitude value. Is always going to give a positive value. So therefore always you have to take the amount of the poles. So therefore we can say, finally I can say that in the case of the Laplace transform, the ROC is bounded by the poles. In the case of Laplace transform, the ROC won't include the poles and is always bounded by the poles. Whereas in the case of Z transform, the ROC is bounded by the amount of the poles, and it won't consider the amount of the poles. So this point I am trying to tell you. Let me write this important point. The ROC is not considered ROC is not include, it does not include the poles. It does not include the poles and bounded by and bounded by and bounded by poles in Laplace transform. In Laplace transform. So ROC is not include the poles but bounded by poles in Laplace transform. Whereas in this case the ROC is not include, is not going to include the magnitude of the poles. Magnitude because of radius, magnitude of poles, but bounded by magnitude of the poles. Magnitude of poles in jet transform. So this is a point always you have to keep in mind. So in the case of Laplace transform, the ROC is not going to include the poles, but it is going to be bounded by the poles. Whereas in the case of jet transform, the ROC is not going to include the magnitude of the poles, but it is going to be bounded by the magnitude of the poles. So finally, I can say only one important point, which is the ROC is not going to include the poles and is going to bounded by the poles in the case of Laplace transform. But in this case, the ROC is not include the magnitude of the poles, but is going to bounded by the magnitude of the poles. They take as it is poles here, they take the magnitude of the poles. This is the only difference. So finally I can say the ROC is not include the poles and is bounded by the poles in the case of Laplace transform. Whereas here the ROC is not include the magnitude of the poles and is going to bounded by the magnitude of the poles in the jet transform. The next point is, for right-sided signals, the ROC is right-sided for Laplace transform. For right-sided signals, the ROC is right-sided for Laplace transform. This f of t is equal to 0 for t less than 0. For left-sided signals, the ROC is left-sided for Laplace transform. So f of t is equal to 0 for t greater than 0. For right-sided signals, the ROC is outward from a particular circle in jet transform. So f of n is equal to 0 for n less than 0. For left-sided signals, the ROC is inward direction for the particular circle in jet transform. So f of n is equal to 0 for n greater than 0. So what is the meaning of this one? Let me tell you. So for right-sided signal, what is the meaning of right-sided signal? When f of t is equal to 0 for t less than 0, then we say those signals are right-sided signals. Then the ROC is right-sided for Laplace transform. Means ROC is always to the right side. The ROC is always to the right side. It is always to the right side. ROC is always the right side to the right side. Right? It is always to the right side of the S-plane. Means in the RHS, it is going to lie in the RHS. For left-sided signals, the ROC is left side of Laplace transform. Means f of t is equal to 0 for t greater than 0. If f of t is equal to 0 for t greater than 0, means we say it is a left-sided signal. So definitely the ROC is basically in the left side for the Laplace in the Laplace transform. For right-sided signals, the ROC is outward from a particular circle in the jet transform. So when f of n is equal to 0 for n less than 0, we say it's the right-sided signal. For left-sided signal, the ROC is inward direction from a particular circle in the jet transform. So f of n is equal to 0 for n greater than 0. So let me explain this point in a very detailed manner so that we can easily able to understand. Suppose I am going to take a right-sided signal in the time domain. So what is the meaning of right-sided signal? F of t is equal to 0 for t less than 0, then we say it is a right-sided signal. So when f of t is equal to 0 for t less than 0, then we say the signal is said to be right-sided signal. Then what is going to happen? I've already told you f of t is equal to 0 for t less than 0 means it is a right-sided signal. It is a right-sided signal. Then what is the ROC? The ROC is always to the right half of the, the ROC is always to the right-sided for Laplace transform. It is always to the right-sided for the Laplace transform like this. It will be always right-sided. It will be always towards the right-sided. Similarly, suppose if the signal is left-sided signal, what is the meaning of signal? F of t is equal to 0 for t greater than 0, then we say it is said to be a left-sided signal. Then what is the ROC? The ROC is nothing but it to the left side. It is also toward the left side. It is always toward the left side of the S-plane. So this also to the left side of the S-plane. Similarly, you take for the you take for the discrete time, not discrete time, for the right sided signal. So what is the meaning of this one? For the right sided signal in the case of discrete domain, so f of n is equal to 0 for n less than 0. And what is ROC? The ROC is always output for a circle. It is always output for a circle. It is always output of a circle. Suppose if it is a left-sided signal, in the case of discrete time domain, then f of t is equal to 0 for t greater than 0. So then what is the ROC? ROC is inward the circle. It is inside the circle. So finally, I can tell you the point. If it is a right-sided signal, means f of t is equal to 0 for t less than 0, or f of n is equal to 0 for n less than 0. Then what is the thing here? It is a right side. It is a right side of S-plane. Right side of S-plane. Or we can say it is outward of a circle. Similarly, suppose if it is a left-sided signal, means f of t is equal to 0 for t greater than 0, or f of t is equal to 0, or f of n is equal to 0 for n greater than 0. Then we can say it is a left side of S-plane. It's a left side of S-plane. And it is inward of a circle. So this is what I am trying to tell you. So if the signal is right sided, means in the time domain it is a right side of the S-plane, and here it is a outward of a circle. Here for the left side of the S-plane means is a left side of the signal means left side signal means is left side of the S-plane or inward of a circle. So this is what I am trying to tell you. So this is the right side of the S-plane, left side of the S-plane, outward of the circle and inward of the circle. Just by seeing the ROC, we can tell what type of signal it is. Suppose similarly what we can say, suppose if the ROC is like this, in the case of if it is going to lie between a small amount of strip, then we can say it is a both-sided signal in a time domain. Suppose if it is going to lie between two circles, if the ROC is going to lie between the two circles, then we can say it is also both-sided signal in the case of the discrete domain, and this is the case of the time domain. So this you can see clearly here from this picture. So if in the case of the S-plane, if the ROC is toward the RHS of the S-plane, then definitely we can say it is a right-sided signal. And similarly, here, in the case of the S-plane, if the ROC is toward the left half of the S-plane, then we can say the signal is said to be left-side signal in the time domain. Suppose in the jet-plane, if the ROC is outward a circle, then we can say the signal is said to be right-sided signal in the discrete time domain. Suppose in the jet plane, if the ROC is inside the unit, if it is inside the circle, then we can say that the discrete time domain is a left-sided signal. Same thing I have concluded. Suppose if the ROC is going to lie between two strips, we say it is a right-sided signal in the time domain. And here, if it is going to lie between the two circles, if the ROC is lying between the two circles, then we can say it is a right-sided signal in the discrete time domain. So these things always you have to keep in your mind. So same thing I have written for right-sided signals means f of t is equal to 0 for t less than 0. The ROC is going to the right-sided of the S-plane. For left-sided signals means f of t is equal to 0 for t greater than 0. The ROC is always basically to the left side of the S-plane. Similarly, in the case of discrete time domain, if the right-sided signal means f of n is equal to 0 for n less than 0, the ROC is always outward of a particular circle in the Z transform. Similarly, for left-sided signal means f of n is equal to 0 for n greater than 0, the ROC is inward direction of a particular circle in the case of the Z transform. So just by seeing the ROC, we can comment on the type of the signal which is there. So just by seeing the signal also, we can comment on the ROC. By seeing the ROC also, we can comment on the type of the signal. So listen carefully. By seeing the signal, we can comment on the ROC, and also by seeing the ROC also we can comment on the signal. So this point always you have to keep in your mind. So now the next point is, if the ROC of Laplace transform includes j omega axis, then the Fourier transform of the signal is going to get exist. If the ROC of the Z transform is going to get include, it is going to include the unit circle, then the discrete time Fourier transform of the signal is going to get exist. So this point I have already told you so many number of times, so let me explain here. See, basically, I have already told you, suppose ROC, if the ROC is going to include, if the ROC of the Laplace transform, if it is going to include the j omega axis, then we can say the Fourier transform is going to, the continuous time Fourier transform is going to get exist for the signal. If the ROC of the Z transform, if it is going to include the unit circle, then the discrete time Fourier transform of the signal is going to get exist. I have already told you f of omega is equal to f of s, and s is equal to sigma plus j omega. If sigma is equal to 0, so 0 plus j omega. So here replace sigma by 0, so therefore we are going to get, in the place of s, if we substitute j omega, we are going to get continuous time Fourier transform. Similarly, in the case of discrete time domain, f of omega is equal to f of z, and replace z is equal to 1 into the power of j omega. In place of z, if you substitute 1 into the power of j omega, we are going to get the discrete time Fourier transform. So this point I have already told you so many number of times, right? So listen carefully. What I am trying to tell you. See, in the case of Laplace transform, if you substitute s is equal to j omega, we are going to get the continuous time Fourier transform. In the case of Z transform, if you substitute s is equal to 1 into the power of j omega, then we are going to get discrete time Fourier transform. So what is the meaning of this one? Suppose if the ROC, in the case of continuous, in the Laplace domain, if the ROC is going to consider the imaginary axis, then default we can say the continuous time Fourier transform for the signal is going to get exist. Suppose if the Z transform, if the ROC is going to consider the unit circle, then we can say a discrete time Fourier transform for the signal is also going to get exist. So finally, I can say if the ROC in the case of Laplace transform, if it is going to include the j omega axis, then the continuous time Fourier transform for the signal is going to get exist. Similarly, if the ROC in the case of Z transform, if it is going to include the unit circle, then the discrete time Fourier transform for the signal is also going to get exist. So this point always you have to keep in your mind. So finally I can say that in the case of the Laplace transform, if the ROC is going to include the imaginary axis, then the continuous time Fourier transform for the signal is going to get exist. Similarly, here in the case of Z transform, if the ROC is going to include the unit circle, then the discrete time Fourier transform for the signal is going to get exist. If it is not including this will not exist. If it is not going to include this, it is also not going to exist. So finally I can say, if the ROC of the Laplace transform, if it is going to include the imaginary axis, then only the Fourier transform, the continuous time Fourier transform for the signal is going to get exist. Similarly, here, if the ROC of the Z transform, if it is going to include the unit circle, then the discrete time Fourier transform for the signal is going to get exist. So this point always you have to keep in your mind. Same thing I have written here. The next point is here. The f of omega is equal to f of s. In place of s, if you substitute j omega, I have already told you. In place of s, if you substitute s is equal to j omega, we are going to get the continuous time Fourier transform. In place of z, if you substitute z is equal to 1 into e to the power of j omega, then we are going to get discrete time Fourier transform. So in place of s, if you substitute s is equal to j omega, we are going to get the continuous time Fourier transform for that signal. In place of z, if you substitute z is equal to 1 into e to the power of j omega, we are going to get the discrete time Fourier transform. So again I can say that if the ROC of the Laplace transform, if it is going to include the imaginary axis, then the continuous time Fourier transform for the signal is going to get exist. Similarly, if the ROC of the Z transform, if it is going to include the unit circle, then the discrete time Fourier transform for the signal is going to get exist. So this point always you have to keep in mind. Now we are going to discuss another important point, which is basically you can see the Fourier transform of the discrete time signal is called as the DTFT, whereas the Fourier transform of the continuous time signal is called as the continuous time Fourier transform. So this is a basic point. So therefore, whenever you are going to the Fourier transform of discrete time signal, that is called as a discrete time Fourier transform, which is TDFT. And the Fourier transform of the continuous time signal is called as the continuous time Fourier transform. So this I am not going to explain, but it may clear this point, which is whenever you are going to the Fourier transform of the discrete time signal, that is called as a discrete time Fourier transform. Similarly, the Fourier transform of the continuous time signal is basically called as the continuous time Fourier transform. So finally I can say, whenever you are going to the Fourier transform of the continuous time signal, which is basically called as a continuous time Fourier transform, whereas whenever you are doing the Fourier transform of the discrete time signal, that is called as the discrete time Fourier transform, which is DTFT. So now let me discuss the other point, which is, so for f of n, if you are going to apply the discrete time Fourier transform, that we are going to get f of omega is equal to sigma n is equal to minus m to plus m to f of n into e to the power of minus j omega n. So for f of n, if you are going to apply z transform, f of z is equal to sigma n is equal to minus m to plus m to f of n into z to the power of minus n. I already told you, in the place of z transform, z, if you replace z is equal to the power of j omega, then we are going to get the discrete time Fourier transform. Same thing I told you, right? In place of z, if you substitute e to the power of j omega, then we are going to get this expression. So therefore, in the place of z transform, if you substitute z is equal to e to the power of j omega, we are going to get the discrete time Fourier transform. So this is what I am trying to tell you. So let me clear this one. So let me write some important points again. See, I have already told you, which is in the discrete time domain, the discrete time Fourier transform is equal to f of z. In place of z, if you substitute z is equal to 1 into e to the power of j omega, then we are going to get the discrete time Fourier transform. So you know what is f of z? F of z is equal to sigma n is equal to minus infinity plus infinity f of n into e to the power of minus n. In place of z, if you substitute e to the power of j omega, then we are going to get, this is z, the discrete time Fourier transform, which is n is equal to minus infinity plus infinity f of n into e to the power of j omega means minus j omega n. So therefore, this is called as a discrete time Fourier transform of the signal f of n, and the previous one is called as the z transform of the f of n. So this point always you have to keep in your mind. In the same fashion, if you go for the Laplace domain also, where f of omega is equal to, in place of s, in the f of s, in the place of s substitute, s is equal to 0 plus j omega, or s is equal to j omega. So you know f of s is nothing but f of s, you know, which is integration from t is equal to minus infinity to plus infinity f of t into e to the power of minus st into dt. So what is the Fourier transform f of omega? The Fourier transform, the continuous time Fourier transform, in place of s, if you write j omega, then we are going to get the Fourier transform, right? So it is equal to minus infinity plus infinity f of t into which is e to the power of minus j omega t dt. And I have already told you, if you are going to compare these two things, what is the common thing that, if you are going to compare these two things, so if you compare these two things, what we can say, so if we compare these two things, integration is replaced by summation and t is replaced by n, and then that is nothing but e to the power of s. So you can write like this, right? E to the power of s over the power of minus t. So t is nothing but n. So e to the power of s is nothing but z. So that is what we said. Z is equal to e to the power of s. S is equal to sigma plus j omega. So we are going to e to the power of sigma into e to the power of j omega. E to the power of sigma is nothing but r into e to the power of j omega. So r is nothing but modulus of z. So these points always you have to keep in mind. So therefore we can say that this is regarding the f of n, and this is regarding the continuous time domain, and this is about the discrete time domain. So in the z transform, if you substitute is equal to e to the power of j omega, we are going to get the discrete time Fourier transform. In this case, if you substitute is equal to j omega, then we are going to get the continuous time Fourier transform. I have given the relations also. So this is called the discrete time Fourier transform on the signal f of n, and this is called as a continuous time Fourier transform of the signal f of t. So these things always you have to keep in your mind. So now listen carefully. Now let's go for the other point. If ROC of f of n includes unit circle, then the DTFT of the f of n is defined. Otherwise it is not defined. Same thing I already told you. See, whenever the ROC of the f of n, if it is going to include the unit circle, then definitely we can say the discrete Fourier transform for the signal f of n is going to get defined. Otherwise, it is not going to get defined. This point I have already told you. See, whenever the ROC of the f of t, so whenever the ROC of the f of t, if it is going to include the imaginary axis, then only the continuous time Fourier transform of the signal f of t is going to get exist. Otherwise, it is not defined. Similarly, if the ROC of the f of n, if it is going to include the unit circle, then the discrete Fourier transform of the signal f of n is going to get defined. Otherwise, it is not going to get defined. So this point also I have already told you. So finally, I can say if the ROC of the f of t, if it is going to include the imaginary axis, then the continuous time Fourier transform of the signal f of t is going to get defined. Otherwise, it is not defined. Similarly, if the ROC of the f of n, if it is going to include the unit circle, then the discrete time Fourier transform of the signal f of n is going to get defined. Otherwise, it is not defined. And I have already told you CTFT is nothing but continuous time Fourier transform, and EDFT is called the discrete time Fourier transform. This is just a notation, right? I have already told you CTFT means continuous time Fourier transform and EDFT means discrete time Fourier transform. So now the next point is, if h of t is the impulse response of the LTI system, if h of t is the impulse response of an LTI system, the LTI system is stable when the absolute integration of the h of t, if it's a finite value, or the then only we can say the system is said to be LTI. It is said to be stable. Means that when the h of t is absolutely integrable, then only we can say the system is stable. Then I've already told you the Fourier transform is going to get exist when the signal is absolutely integrable. When the signal is absolutely integrable, then also we can say the Fourier transform is going to get exist. Then also the Fourier transform is going to get exist. So if you see clearly, if the system is stable means, the Fourier transform is also going to get exist. If the Fourier transform is going to get exist means the system is also stable. So h of t Laplace transform is h of s. H of t Fourier transform is h of omega, as I have already told you. If Fourier transform of the h of t is exist, then LTI system is absolutely stable. So we can say if the Fourier transform of the h of t exists means then the LTI system is absolutely stable. If ROC of h of s includes the geometric axis in S plane, then LTI system is stable and the Fourier transform is going to get exist. So what is the meaning of this one? Suppose for a given LTI system, take the impulse response, this h of t. So h of t Laplace transform is h of s and h of t Fourier transform is h of omega. So now what I will do, the LTI system is stable when the h of t is absolutely integrable. When the h of t is absolutely integrable, then only we can say that the system is said to be stable. Similarly, the Fourier transform for the h of t is going to exist only when the signal is absolutely integrable, which is h of t is absolutely integrable. So we can say, suppose if the Fourier transform for a signal h of t exists, means definitely we can say the system is stable. Or we can do vice versa also. If the system is stable, then definitely the continuous time Fourier transform for the signal is also going to get exist. So therefore we can say if Fourier transform for h of t exists, then LTI system is stable. If ROC of the h of s is going to include the geometric axis in S plane, then the LTI system is stable and the Fourier transform is also going to get exist. So finally, I can say only one important point. So listen carefully. Let me give the conclusion. In the continuous time domain, I will try to give the conclusion. So in the continuous time domain, CT is continuous time domain and is the discrete time domain. So let me give the conclusion, each and everything. Suppose if h of t is absolutely integrable. If h of t is absolutely integrable, it is absolutely integrable. So what is the meaning of this one? Absolutely integrable means we can say integration from t is equal to minus ∞ plus ∞ mod of h of t dt. If it is less than infinity means it's going to be a finite value. So therefore we can say it is absolutely integrable means we can say the LTI system is a stable system. It is a stable system and the Fourier transform for continuous time Fourier transform of h of t is going to get defined. It is going to get defined. So listen carefully. So you can say for a signal h of t, h of t is nothing but impulse response. It is absolutely integrable. Then we can say the LTI system is absolutely stable, as well as the Fourier transform of the h of t is also going to exist. So we can say, suppose if we have figured out the ROC of the h of s, so if we figure out the ROC of the h of s is the Laplace transform of the h of t. If it is going to include the j omega axis, then what we can say, the system is absolutely, the Fourier transform is going to exist. If the Fourier transform is going to exist, then the system is also stable. So this point always you have to keep in mind. So if a system is stable, the Fourier transform is also going to exist. Is also going to both. We can say one is going to exist, the other is also going to exist. So therefore, we can say if the ROC of the h of s is going to include the imaginary axis in the s plane, then the Fourier transform is going to exist. When the Fourier transform is going to exist, means the system is also stable. The system is also stable. Same thing for the discrete time domain. So what we can say here, h of n is absolutely integrable, summable, absolutely summable. So if h of n is absolutely summable, then what we can say, same thing here, sigma n is equal to minus infinity to plus infinity mod of h of n. If it is less than infinity, then we can say the LTI system is said to be stable, as well as the discrete time Fourier transform here, continuous time Fourier transform of the h of n is going to get defined. It is going to get defined. So therefore we can say that whenever the h of n is an impulse response of a system, it is absolutely summable, then the LTI system is said to be stable, as well as the discrete time Fourier transform of the h of n is also going to get defined. So what we can say finally, suppose if the ROC of the h of z, if it is going to include the unit circle, then what we can say, a discrete time Fourier transform is going to exist, and also the system is said to be stable. So if one is going to exist, the other is also going to exist. So this is what I am trying to tell you. So in the case of the if the ROC of the h of z is going to include the unit circle, then in the z plane, then definitely the discrete time Fourier transform for the signal is going to exist, and also we can say the system is said to be stable. So this is what I can easily say from this one. So now the next thing is here, the next thing I can say, which is LTI system is causal when h of t is equal to 0 for t less than 0. I have already told you what is the meaning of system is LTI system is said to be causal when h of t is equal to 0 for t less than 0, because the output is going to is independent of the future values of the input. The present output is independent of the future values of the input, means the h of t is equal to 0 for t less than 0. Then only we can say that the LTI system is said to be causal. So for h of t, if you try to find the Laplace transform, we are going to get the h of s. So h of t is the right-sided signal, because h of t is equal to 0 for t less than 0. So h of t is a right-sided signal. So ROC of the h of s is a right-sided. So whenever the h of s is a right-sided, so definitely we can say that it is a right-sided signal. It is a right-sided signal. So I can say only one important point. Suppose if you take an LTI system which is causal means h of t is equal to 0 for t less than 0. Then if you try to find the Laplace transform of h of t, we are going to get the h of s. So as the h of t is a right-sided signal, so its ROC is also right-sided. So h of t is a right-sided signal, so its ROC is also right-sided. As I already told you, if the signal is left-sided, the ROC is left-sided. If the signal is right-sided, then the ROC is also right-sided. If the signal is both-sided, means the ROC is between the strips. I have already told you this point, so listen carefully. If the signal is left-sided, means the ROC is to the left-sided. If the signal is right-sided, means the ROC is also right-sided. Suppose if the signal is both-sided, means the ROC is going to differ between the two strips. So in this case, if you want the LTI systems to be causal, then the impulse response should be 0 for t less than 0. Means we can say the impulse response is if the h of t is basically a right-sided signal, so its ROC, h of s ROC is also towards the right-sided in the S plane. So this is what I am trying to tell you. Similarly, in the case of the discrete time domain also, we can say LTI system is said to be causal when h of n is equal to 0 for n less than 0. So for h of n, the z transform is h of z. Then h of n is a right-sided signal, so its ROC of the h of z is also right-sided. Same fashion we have to go for the discrete time domain also. So these things always you have to keep in your mind. So right sided means it is outward the circle. It is outward the circle. So we can say simply in the continuous time domain, if the signal is left sided means the ROC is left sided. If the signal is right sided means the ROC is also it's also right sided. If the signal is both directional means then we can say ROC is between the strips. Whereas in the discrete time domain, if the signal is left sided means the ROC is the inverse of a circle. If the signal is right sided means the ROC is outward of a circle. If the signal is bidirectional means we can say with the both side signal means the ROC is between the two circle strips. Between the two circles only it is going to get present. So these things I have already told you so many number of times. Now we are going to discuss the other point, which is LTI system is causal and stable when the ROC of the H of S is shown below. So LTI system is said to be causal as well as stable when the ROC of the H of S is shown below. So I have already told you LTI system is causal means when the impulse response H of t is equal to 0 for t less than 0. And stable means I have already told you the absolute iteration of the means the H of t is absolutely iterable. Then only you can say the system is stable. So here this system is both the causal as well as stable means H of t is equal to 0 for t less than 0 as well as the H of t is absolutely iterable. Then what is the consequences which are going to happen? Let's see the ROC. So for H of t, the Laplace transform is H of S. So now, if you see clearly here, so this is the ROC of the H of S that we are going to get. So this is the S plane. So we can see this is the ROC which is going to happen. So in this poles can lie. So in this region the poles can lie. I've already told you the ROC will never include the poles. But it is bounded by the poles, but it never include the poles. I've already told you because ROC means this is if you keep any value of this one in that f of s, you should get a finite value, but if you keep a pole, you are going to get infinite. So in this region the poles can lie, but in this region there will be no poles, and this ROC is bounded by the poles. So you can say this is the ROC of the H of S. Why it is like this? If you see, I've already told you here H of t is equal to 0. So let me write the point here. H of t is equal to 0 for t less than 0. Then the system is said to be causal and is absolutely summable. Integration from t is equal to minus infinity plus infinity mod of H of t dt. This should be finite value. Then we can say it is both causal as well as it is both stable. Then I've already told you here the signal is right sided signal. So ROC should be right sided. So this is right sided, right? So this is right sided. So now here it is absolutely stable. So absolutely stable means I've already told you if it is stable means it should also include the Fourier transform should also exist. So therefore the ROC should contain the imaginary axis. Then only we can say that it is going to happen like this. So we can say whenever the LTI system is causal as well as stable, then we can say the H of t is a right sided signal. So ROC should be right sided, and also the system is stable means the H of t is absolutely integrable. It means that the Fourier transform is also going to exist. So therefore we can say the ROC should even include the j omega axis. So finally I can say that if a given LTI system is said to be causal as well as stable means the impulse response is a right sided signal means H of t is equal to 0 for t less than 0, and as well as the LTI system is stable means it is absolutely integrable. So if the signals are absolutely integrable, then definitely the Fourier transform is also going to exist. If the Fourier transform is going to exist means the ROC should also include the imaginary axis. So therefore this is the region of the ROC. So you can see the ROC is right sided as well as the ROC is going to include the imaginary axis, and here the poles can lie and is bounded by the poles. So this is what we can say. Finally, by seeing this ROC we can say the H of t is a right sided signal as well as it is going to include the imaginary axis. The system is absolutely stable also. So this is what we can say. So therefore we can say as the ROC is the right sided. So definitely we can, by seeing the ROC we can say as the ROC is right sided. So So this is h of s. So this is the ROC of the h of s. So by seeing this ROC, what we can commit that the h of t signal is a right sided signal, because the ROC is it is right sided, means h of t is equal to 0 for t less than 0, and as well as this ROC is going to include the imaginary axis. So it is the Fourier transform is going to get exist. If Fourier transform exists, the system is stable. So therefore we can say it is absolutely summable and it is absolutely integrable. So therefore this is what we can say by seeing the ROC. So now the next thing is, if h of n is the impulse response of the LTI system. LTI system is stable when when the h of n is absolutely summable, and h of omega is going to exist when the h of n is absolutely summable. I've already told this point. Same thing for time domain as well as the discrete time domain. Suppose if you take h of n, which is the impulse response of an LTI system, discrete time LTI system. Suppose if you want the system to be stable, if you want the LTI system to be stable, then h of n should be absolutely summable. Similarly, if you want the Fourier transform to exist for h of t, then the signal h of n should be also absolutely summable. It should be absolutely summable. So definitely, if the h of n is absolutely summable, means the system is said to be stable, as well as the Fourier transform is also going to get exist, means the discrete time Fourier transform. So if the discrete time Fourier transform for h of n is going to get exist, means by default the LTI system is said to be stable. So if the ROC of the h of z is going to include the unit circle, then the LTI system is stable. So finally, I can say that for a given LTI discrete time LTI system, for impulse input, we are going to get the impulse response h of n. Suppose if it is absolutely summable, by default we can say the LTI system is stable, as well as the Fourier transform is going to get exist. So what we can say? Simply, if you try to find the ROC for the h of n, means if you try to figure out the h of z and you try to find the ROC, then definitely the ROC should include the unit circle. So if it is going to include the unit circle, means by default discrete time Fourier transform is going to get exist. If discrete time Fourier transform is going to get exist, means by default the system is also stable. So therefore, finally, if the discrete time Fourier transform for the h of n is going to get exist, means by default we can say the LTI system is said to be stable, as well as if the ROC of the h of z is going to include the unit circle, then the LTI system is stable. So finally, I can say only one thing. Suppose if you are taking a discrete time LTI system, and if you are for given impulse to be v, we are going to get the impulse response h of n. So if the h of n is absolutely summable, then by default we can say the given LTI system is stable, as well as the discrete time Fourier transform for the h of n is going to get exist. So if one is going to exist, means the other is also going to get happen. So for h of z, if you try to find the ROC, it is going to include the imaginary axis. So what we can say, it is going to include the imaginary axis, means by default we can say the LTI system is stable. If it is stable, means the Fourier transform is also going to get included. So this is what I am trying to tell you. The next point is, the LTI system is causal when h of n is equal to 0 for n less than 0, and for h of n, this is the Z transform. This is the h of z, means this is the Z transform. So small correction here. So let me correct this part. So this is basically Z transform, not h of. So let me rub this part. So let me rub this one. So now let me write this is the Z transform for h of n. The Z transform is h of z, right? So let me write here. This is Z transform. So for h of n, the Z transform is h of z. If h of n is a right-sided signal, so ROC of the h of z is outward directed. So what I am trying to tell you is very simple. Say, suppose for a given LTI system, I am going to assume the given LTI system is said to be causal. It is a causal, means the impulse response h of n is equal to 0 for n less than 0. Then if you try to find the Z transform for the h of n, we are going to get the h of z. So definitely we can say h of n is a right-sided signal. If h of n is a right-sided signal, the ROC is also a right side. It is outward the circle. It is outward a circle. It is outward a circle. So therefore, suppose if h of n is a left-sided signal, means the ROC is inward of a circle. If the h of n is a both-sided signal, means the ROC is going to lie between the two circles. I already told you. So therefore, we can say finally, suppose if you consider an LTI system, this is basically a causal system. Then h of n is equal to 0 for n less than 0. Definitely we can say it is a right-sided signal. So for h of n, you try to find the h of z, and if you figure out the ROC of the h of z, it is basically outward of a circle, because the h of n is a right-sided signal. So ROC is also outward of a circle. So these points always you have to keep in your mind. Now we are going to discuss another point. Listen carefully. The LTI system is causal and stable when the ROC of the h of z is shown below. So basically what they are given is, suppose they are given an LTI system, which is causal as well as a stable. Then they are given the ROC of the H of Z, which is given below, they have given. So what is that meaning? We are going to discuss. This concept just now we have discussed in the continuous time domain. Let's discuss in the discrete time domain also. So causal means I've already told you. What's the meaning of causal? When H of n is equal to 0, for n less than 0, and we can say it is a causal system. So LTI system is said to be causal when H of n is equal to 0 for n less than 0 means it is a right-sided signal. So ROC is towards the right side, it means outward of a circle. And here it is also stable. Stable means absolutely integrable, means H of n is absolutely integrable. This minus into plus infinity, mod of H of n is less than infinity. So therefore we can say, as H of n is absolutely summable, definitely we can say the system is said to be stable. If it is absolutely summable, the discrete and Fourier transform is also going to get exist. So if you want discrete and Fourier transform to exist, the ROC of the H of Z should also include the unit circle. So therefore we can say, if you want a system, LTI system to be causal as well as stable, the ROC is basically towards outward of a circle, and also it should include the unit circle. So you can see clearly here. So this is a unit circle. So this is a unit circle. So from this, the ROC is outward. It is outward. So definitely the ROC is going to include the unit circle as well as it is outward. So whenever it is outward, means the signal is a right-sided signal. Means H of n is equal to 0 for n less than 0. And also it is going to include the unit circle, means the discrete time Fourier transform is going to get exist. Means it is going to exist when H of n is absolutely summable. If H of n is absolutely summable, the system is also stable. So therefore we can say that. So therefore we can say this is the ROC that we can get when the LTI system is causal as well as stable. So for H of n, the Z transform is H of Z. So in this area, poles may present here. So only in this region, poles have freedom to lie in this region. So only in this region, the poles have freedom to lie. Suppose if they are going to lie in ROC, means it will never lie, because if they are going to lie, so what's the meaning of ROC? If you substitute those points in the H of Z, it should get a finite value. But if you substitute those poles, we are going to get infinite value. That is the reason in this region, the poles have the freedom to lie. So only in this region, the poles have the freedom to lie in this region. Same concept I have already told you for the continuous time domain. So finally I can say, suppose if you take a discrete time LTI system is causal as well as stable, so what is the meaning of that one is very simple, which is it is a causal, means we can say H of n is equal to 0 for n less than 0, means it's a right-sided signal. And it is stable, means H of n is absolutely summable. If H of n is absolutely summable, the discrete time Fourier transform is also going to get exist. So if you try to find the Z transform of H of n, we are going to get H of Z. And if you try to find the ROC, we are going to get in this fashion, which is the ROC is always outward and it should include the unit circle. So you can see clearly in this fashion, the ROC is outward and also it is going to include the unit circle. So because of this, what is going to happen? As the ROC is outward, the H of n is a right-sided signal, means H of n is equal to 0 for n less than 0. And also it is going to include the unit circle. So you can say the discrete time Fourier transform is going to exist. If the discrete time Fourier transform is going to exist, means the H of n is absolutely summable. So therefore the LTI system is also stable. So this point always you have to keep in your mind. Same concept we have already told for the continuous time domain case also. So now let's go for the other point. Suppose the ROC of the right-sided signal starts from the rightmost pole. The ROC of the right-sided signal starts from the rightmost pole. So what is the meaning of this one? So if you go for the continuous time domain, I am telling this concept for the continuous time domain. The ROC of the right-sided signal starts from the rightmost pole. So listen carefully, what is the meaning of this one? Suppose let me take a signal f of t. Suppose let me take a signal f of t. F of t is equal to 0 for t less than 0. So this is called as the right-sided signal. So definitely then what is ROC? ROC of f of s is a right-sided. It is a right-sided. I have already told you it is also right-sided. So here for f of s, suppose you got the poles like this one. The poles like minus sigma 1, minus sigma 2. Suppose let me take some values. So minus 2, minus 3, some 1 and 2. Like this we have got poles, right? So let me draw on the S plane. So let me draw on the S plane. So this is a sigma and this is a j omega. So the poles are always, you got all the real values only you got. So one is minus 2 here. So minus 2 here. here minus 3 is here, and here 1 here, and here 2 here. And what we know, as signal is right sided signal, the ROC is also right sided. So this point I already told you, as a signal is right sided, so definitely as a signal is right sided signal, the ROC is also right sided. So for where means from here. So from here the ROC is going to get included. So this is the ROC. From here it is going to get included. So therefore we can say ROC of the right sided signal, it starts from the rightmost pole. From the rightmost pole. Suppose if it is a left sided signal, then what is going to happen? Listen carefully. Suppose if f of t is equal to 0, but t greater than 0. So what is the meaning of this one? It's a left sided signal. So I try to find the f of s or f of t. Then this ROC is having a left sided ROC. Same thing. So poles are suppose minus 2, minus 3, 1, 2. Then where is the ROC is going to get like? So do the same thing here. Minus 2, minus 3, 1 and 2. So if you try to find the ROC, here the ROC will be in this fashion. So the ROC is left sided and it is towards the least pole. Here towards the highest pole, but here towards the rightmost pole and is the leftmost pole. So finally I can say the ROC of the right sided signal starts from the rightmost pole and the ROC of the left sided signal starts from the leftmost pole. So this is a point you have to keep in your mind. So ROC of the ROC of the right sided signal starts from the rightmost pole and the ROC of the left sided signal starts from the leftmost pole. So this is the point I am trying to tell you. So finally I can say the ROC of the right sided signal starts from the rightmost pole and the ROC of the left sided signal starts from the leftmost pole. So these points always you have to keep in your mind. So now the next point is f1 of t either plus or either minus or either into or either division of f2 of t. Then ROC of the net signal is the common range of all the ROCs together. So what is the meaning of this one? Suppose if there is f1 of t and there is f2 of t, between these two things either you can perform addition or either you can perform subtraction or either you can perform multiplication or either you perform division. Then ROC of the net signal is the common range of all the ROCs together. This point I already told you so many number of times, but let me explain again. Suppose you take a signal f1 of t. Suppose you take the signal f1 of t. So for f1 of t, the Fourier, the Laplace transform is f1 of s with an ROC 1. Suppose f2 of t is there. For this the Laplace transform is f2 of s and here the ROC is ROC 2. Suppose we are performing a new signal f1 of t, either addition or either subtraction or either division or either multiplication or division of f2 of t. Then what is the overall Laplace transform? Same thing, f1 of s or either addition or either subtraction or either multiplication or either division with f2 of s. Then what is the net ROC? ROC is nothing but common ROC because in this common ROC only f1 of s is going to get defined and f2 of s also is going to get defined only in this common ROC. So you want both the things to define only in the common ROC, it is going to get present. So what is the common ROC? ROC1 intersection ROC2. The common ROC between these two things, remember in this ROC only, these two things are going to get defined. So if these two things are defined, the overall result is also going to get defined. So this is what I am trying to tell you. So your f1 of s is defined only in the ROC1 and f2 of s is defined only in the ROC2. So if you want both these things to define, then the ROC should be common ROC. Then in the common ROC both are going to get defined. If both are defined, the overall thing is also going to get defined. So this point always you have to keep in your mind. So whatever the operation you are doing with the two signals, either addition or subtraction, either multiplication or division, the net ROC of the signal is nothing but it's a common ROC or intersection ROC of the individual signals. So these points always you have to keep in your mind. So between two signals f1 of t and f2 of t, either you can perform addition or either you can perform subtraction or either you can perform multiplication or either you perform division. Then the net ROC of the net signal is the common range or common ROC of all ROCs together. So these points always you have to keep in your mind. The next thing is the ROC of the right sided discrete time signal starts from the rightmost magnitude of the pole. Rightmost magnitude of the pole. So this point I have already told you. Suppose that the ROC of the right sided discrete time signal starts from the rightmost magnitude of the pole. That is magnitude. That is the magnitude of the pole. So listen carefully. Same concept let me tell you for the discrete time domain. Suppose there is a discrete time domain f1 of n. So for f1 of n, this is basically which is a right sided signal. So f1 of n is equal to 0 or n less than 0, this is a right sided signal. So definitely for f1 of n, if you try to find the z transform, we are going to get the f1 of z. So if you try to find the ROC of f1 of z is also right, it is an output. It is an output of a circle. It is output of a circle. So let me draw the picture. So let me draw the picture here. Suppose for f of z, we got some poles. For poles like we got -1, -2, 2, and 1 we got. Suppose you take poles like this you got. Now you have to take only the magnitude. So magnitudes are nothing but 1, 2, 2 and 1. So draw the poles here. So this is a 1 and this is a 2. So now draw these two circles. So this is a 2 circles, right? 2 circles. So out of this is the ROC. So this is the ROC. So it is a ROC. So like this ROC you are going to get. So therefore we can see clearly the ROC of the right side of this signal starts from the rightmost magnitude of the pole. Similarly for the left side signal, so f1 of n is equal to 0 or n greater than 0. So this is a left sided signal. So for this, if you try to find the z transform, we are going to get the f1 of z. Suppose this has the poles like -1, -2, 1 and 2. So I same thing I told you, try to find the magnitude of the poles 1, 2, 1 and 2. So the ROC is nothing but it is inward because it is a left sided signal. The ROC will be inward. So in the z plane, first to plot the poles which are 1 and which are 2. So out of this, which is the least one? The least one is 1. So try this circle of radius 1 and this is the ROC. So this is the ROC. So therefore we can say finally we can say only one important point, which is, so I can say only one thing, which is the ROC of the right sided discrete time signal starts from the rightmost magnitude of the pole. Similarly, the ROC of the left sided discrete time signal starts from the leftmost, we can say least magnitude of the pole. So listen carefully. So listen carefully. So what I am trying to tell you, listen carefully. The ROC of the right sided signal starts from the highest magnitude of the pole. Highest magnitude of the pole. And here the ROC of the left sided discrete time signal starts from the least magnitude of the pole. Please listen carefully. Here let me write here. So let me write the point here. Small correction here. The ROC of the right sided discrete time signal starts from the highest magnitude of the pole. Here highest magnitude of the pole. Similarly, the ROC of the left side discrete time signal starts from the least magnitude of the pole. So this point always you have to keep in your mind. So the ROC of the right sided discrete time signal starts from the highest magnitude of the pole, and the ROC of the left sided discrete time signal starts from the least magnitude of the pole. So this is what I am trying to tell you. So this point always you have to keep in your mind. So next point is the ROC of the left sided continuous time signal starts from the least pole and it is left sided in the Laplace transform. I have already told you the ROC of the left sided continuous time signal starts from the least pole and it is to the left sided in the Laplace transform. I have already told this point, right? I have already told you here. I have already told you this point here. Listen carefully. I have already told you here, right? So when the signal is a left sided continuous time signal, then the ROC is going to lie in the, it starts from the least of the pole, from the leftmost of the pole, we can say. So finally, if I going to conclude the two concepts, listen carefully. The ROC of the right sided continuous time signal starts from the rightmost pole. Similarly, here the ROC of the left sided continuous time signal starts from the leftmost pole. So this is a point I am trying to tell you. So listen carefully. Here we can say the ROC of the right sided continuous time signal starts from the rightmost pole, whereas the ROC of the left sided continuous time signal starts from the leftmost pole. So this point always you have to keep in your mind. So finally I can say the ROC of the right sided signal, it starts from the rightmost pole and it's toward the towards the right, towards the ROC is toward the right side. And similarly here, and similarly here, for the ROC of the left side continuous time signal, it starts from the leftmost pole, and the ROC is toward the left side, and ROC is toward the left side. So finally, I can say, conclude that the ROC of the right side continuous time signal starts from the rightmost pole, and the ROC is toward the right side. Similarly, for the ROC of the left side continuous time signal starts from the leftmost pole, and it's toward the ROC is toward the left side, as you can see clearly from this picture. The next point is here. The ROC of the left side discrete time signal starts from the least pole magnitude, and it is towards the inward, So inward. So let me, at this point I already told you, let me conclude here. In this concept, let me conclude. So let me conclude here. So you can see that the ROC of the left side discrete time signal starts from the least magnitude of the pole, and is towards the inward. Similarly, the ROC of the right side discrete time signal starts from the highest magnitude of the pole, and it is towards the outward. Whereas the ROC of the left side discrete time signal starts from the least magnitude of the pole, and it is towards the inward. So finally, I can say only one thing. So finally, I can say the ROC of the right side discrete time signal starts from the highest magnitude of the pole, and it is outward. Whereas the ROC of the left side discrete time signal starts from the least magnitude of the pole, and it is towards the inward. So these points always you have to keep in your mind. So these 2 points always you have to keep in your mind. So finally, I can say that the ROC of the right side discrete time signal starts from the highest magnitude of the pole, and it is towards the outward. Whereas for the ROC of the left side discrete time signal, it starts from the least magnitude of the pole, and it is towards the inward. So these points always you have to keep in your mind. So now the next thing is, for a two-sided signal, its ROC is bounded, or we can say f of t is not equal to 0 from minus ∞ to less than t less than or equal to infinity. Then we can say it is a two-sided signal, right? Its ROC is bounded, or we can say rectangular strip for a common region of ROC. So we can say for a two-sided signal, what's the meaning of two-sided signals? F of t is not equal to 0 for minus ∞ less than t less than or equal to infinity. And what I told you the definition of two-sided signal. Its ROC is a bounded or rectangular strip for a common region of ROC. And what I told you, suppose a given signal is a bounded signal. Suppose if a given signal is a two-sided signal in a continuous time domain, suppose f of t is not equal to 0 for minus ∞ less than t less than infinity. So this is basically we can say two-sided signal. So this is a two-sided signal. If it is a two-sided signal, then what is the meaning of this one? Then the ROC is a rectangular strip, which it is going to bond between the two poles. It is going to bond between the two poles. So listen carefully. What is the meaning of this one? Suppose f of t, suppose try to find the Laplace transform of f of t, then we are going to get the f of s. And I have figured out the poles for this one. Minus 1, 2. I got like this. So I have got like this. 2 poles I have got. So let me take the poles and explain. Minus 1 and 2. So as this given signal is a, we can say bisided signal. So it is going to lie between the two poles. So this is a ROC. It is going to happen. So this is ROC it will have. So therefore we can say clearly here. So we can see here it is going to lie between the two poles, and it is going to lie between the two poles. So ROC is bounded. It is bounded between the two poles. It is bounded, or we can say rectangular strip also we can say, or for a common region of ROC. So when a given signal is a two-sided signal, which is f of t is not equal to 0 for t raised to minus ∞ plus infinity, then ROC is a bounded, or it is a rectangular strip for a common region of ROC. So simply what I can say. Suppose the given signal is a, we can say it is a two-sided signal, which f of t is not equal to 0 for t raised to minus ∞ to plus 50. Then for f of t, if you try to find the Laplace transform f of s, it is going to lie between the poles. It is going to lie between the poles. It is going to get like this. There's some bonding. The ROC is bonded. It is a bonding between the poles. Rectangle strip also we can say. So these things always you have to keep in your mind. Now we are going to discuss the another point, which is if the rightmost pole of the right sided signal, if it is less than the leftmost pole of the left side signal, and if the highest magnitude pole of the right side signal is less than the least magnitude pole of the left side signal. Here we have right here, not rightmost pole. Here it should be highest magnitude of the pole. Highest magnitude of the pole of the highest magnitude of the pole of the right side signal is less than the least magnitude pole of the left side signal. Then we can say that the ROC is a final rectangular strip as well as 5 angular strip. So what is the meaning of this? So see, this is for the continuous time case and this is for the discrete time case. So if the rightmost pole of the right side signal is less than the leftmost pole of the left side signal, then there will be common region, common ROC. Similarly, if the highest magnitude pole of the right side signal and the least magnitude pole of the left side signal, if this is less than this one, definitely there will be some angular strip between the two things. Then we can say that signal is said to be by we can say that signal is said to be two-sided signal. It's a two-sided signal. So listen carefully. I'm trying to tell you some important point. Suppose you take like this. Suppose let me take a small example so that you can easily able to understand. Suppose it's a right-sided signal and this is a left-sided signal. Suppose right-sided signal has the pole sigma, which is basically its pole is 2, and here the pole is now, let me consider this is 3. Then what is going to happen? So let me draw in the S plane. So this is a 2, and this is a 3, right, in the S plane. So now what I will do, right-sided signal means I have already told you the ROC is towards the right side, it is towards this side. Right? Similarly, for a left-sided signal means the ROC is towards this side. So between this, what is the common ROC? So this is the common ROC. So this is the only common ROC. So this is called as a rectangular strip. Similarly, if you go for the discrete time domain, suppose for the right-sided signal and for the left-sided signal, here the magnitude of the pole, here the magnitude of the pole is 2, and here the magnitude of the pole is 3. Then see carefully, I already told you, which is for right side signal, the magnitude of the pole is 2 we got, and the magnitude of the pole we got 3 here. So now let's go for the Z plane. So this is a circle of radius 2. The radius is 2. As it is a right side signal, so ROC is outward. Similarly, take another circle of radius 3. So this is a radius 3. And here it is a left side signal, so therefore the ROC is inward. So between these two, what is the common ROC? So this is the common ROC. So this is called as the angular strip. So this is angular strip. So this is the angular strip. So angular strip. And here it is a rectangular strip. So what is the meaning of this one? We can say the signal is said to be two-sided signal. The signal is said to be two-sided signal. So these points obviously you have to keep in your mind. So if you have a rectangular strip or the angular strip, default we can say the given signal is said to be a two-sided signal. See, if a signal is not a right-sided signal, if a signal is not a left-sided signal, by default we can consider it said to be both-sided signal. So listen carefully. Suppose they are given some signal. First you have to confirm whether the given signal is right-sided signal or not. What's the meaning of right-sided signal? If the signal f of t is equal to 0 for t less than 0, then we say it's right-sided signal. Confirm this one. Similarly, suppose this is not satisfied. Similarly, go for the left-sided signal. What's the meaning of left-sided signal? F of t is equal to 0 for t greater than 0. If this condition is also not satisfied, means by default the signal is said to be two-sided signal. So, if it is not a right-sided signal or if it is not a left-sided signal, means by default it is a two-sided signal. So, this is what I am trying to tell you. If a given signal is not a right-sided signal, and if a given signal if it is not a left-sided signal, but then by default it is said to be two-sided signal. So, this is what I am trying to tell you. So therefore we can say that, see, in the case of the continuous time domain, If the rightmost pole of the right-sided signal is lesser than the leftmost pole of the left-sided signal, then default we are going to get an angular strip. Similarly, in the discrete time domain, if the highest magnitude of the pole of the right-sided signal, if it is lesser than the least magnitude pole of the least magnitude pole of the left-sided signal, then we are going to get an angular strip. So listen carefully. Here, if the rightmost magnitude of if the rightmost pole of the right-sided signal, if it is lesser than the leftmost pole of the left-sided signal, we are going to get a rectangular strip. Similarly, if the highest magnitude pole of the right-sided signal is lesser than the least magnitude pole of the left-sided signal, then by default we are going to get an angular strip. So finally, I can say that if the rightmost pole of the right-sided signal, if it is lesser than the leftmost pole of the left-sided signal, we are going to get a rectangular strip. Similarly, if the highest magnitude pole of the right-sided signal, if it is lesser than the least magnitude pole of the left-sided signal, then we are going to get an angular strip. Same thing I can say here. If the rightmost pole of the right-sided signal, it is lesser than the leftmost pole of the left-sided signal, then by default we are going to get a rectangular strip. Similarly, if the highest magnitude pole of the right-sided signal, if it is lesser than the least magnitude pole of the left-sided signal, then by default we are going to get a rectangular angular strip. So the ROC is a finite rectangular strip as well as a finite angular strip. So by this we are going to get the finite angular strip, and by this we are going to get a finite angular strip. So these things always you have to keep in your mind. Now we are going to discuss the another point, which is if ROC is finite strip, then compulsory signal is two-sided. See, if the ROC is finite strip, then compulsory signal is two-sided signal in the time domain. So same thing I've already told you. Suppose if ROC is a finite strip, if ROC is a finite strip, then what is the meaning of that one? We can say whatever the given signal is compulsory a two-sided signal. Two-sided signal means I've already told you. First you have to check whether a given signal is right-sided signal or not. If it is not, then go for the checking whether it is a left-sided signal or not. And then if it is not there, if a signal is not the right-sided, not a left-sided, means by default it is a two-sided signal. So therefore, if a signal, if it is not a right-sided and if it is not a left-sided signal, means by default we can say it is a two-sided signal. So what is the meaning of two-sided signal? F of t is not equal to 0 for t less than minus into plus infinity. So this is called as a two-sided signal. So I have already told you, suppose if ROC is a finite strip, in the finite rectangular strip or finite angular strip, definitely whatever the given signal is basically a two-sided signal in the time domain as well as the discrete time domain also. Continuous time domain and discrete time domain, it will be two-sided signal. So two-sided signal means a signal which is not a right-sided signal, a signal which is not a left-sided signal, means by default it will be a two-sided signal. So f of t is not equal to 0 for t less than minus into plus infinity. That is the definition of the two-sided signal. So finally I can say, so just by seeing the ROC, if it's a finite rectangular strip or finite angular strip, then definitely we can say whatever the given signal is basically a two-sided signal in the time domain. So two-sided signal means a signal which is not a right-sided signal, a signal which is not a left-sided signal, then definitely it is a two-sided signal, and its definition is f of t is not equal to 0 for t less than minus into plus infinity. The next point is a continuous time signal with finite amplitudes and finite duration, then ROC will be entirely plane, but excluding sigma is equal to minus 50 or infinity or both based on the type of the finite signal. So listen carefully, a continuous time signal with finite amplitude and finite duration, then ROC will be the entire plane, but excluding the sigma is equal to minus infinity or plus infinity or both based on the type of the signal. So listen carefully, a continuous time signal with the finite amplitude and finite duration. So what is the meaning of this one? Suppose you taken some signal in the continuous time dimension, it has a finite amplitude and finite duration, then ROC will be entire plane. It will be entire plane, but excluding sigma is equal to minus infinity, sigma is equal to plus infinity, or both based on the type of the signal. So what is the meaning of this one? Suppose here, see basically I've already told you what is the meaning of two-sided signal. So two-sided signal I have told you. Two-sided signal means it is going to present for all the time from -infinity plus infinity. That is the definition of a two-sided signal. So two-sided signal means it is present from, say, right-sided signal means f of t is equal to 0 for t less than 0. And left-sided signal means f of t is equal to 0 for t greater than 0. Two-sided signal means f of t is not equal to 0 for all the value of t. Means the signal is present for all the time from -infinity to plus infinity. That is the meaning of two-sided signal. Suppose if you take a finite signal, suppose if you take a continuous time signal which is having a finite amplitude and finite duration, then what is the ROC? Then its ROC will be entire explained. Excluding either sigma is equal to -infinity or plus infinity or both based on the type of the finite signal. So let me write here. So we can say that. So listen carefully. Suppose f of t is having a, so I have already told you, if f of t is equal to 0 for t less than 0, then we can say it is a right-sided signal. If f of t is equal to 0 for t greater than 0, it is called as a left-sided signal. If f of t is not equal to 0 for all t, then we say it is a both-sided signal or two-sided signal. Suppose if f of t is having a finite duration, so small example is like this one. Suppose you take a signal like this. So you can see the signal f of t has a finite amplitude and is present for only finite amount of duration. So for this signal, if you try to figure out the ROC, it will be entire explained. Excluding either sigma is equal to -infinity or plus infinity or both, depending on the type of the finite signal. So we can say that a continuous time signal with a finite amplitude and finite duration, then our ROC will be entire explained, but excluding sigma is equal to -infinity plus infinity or both based on the type of the finite signal. So what I am trying to tell you is very simple. Suppose in the continuous time domain, if you take a signal which is having a finite amplitude and finite duration, then ROC will be entire explained, but excluding either sigma is equal to -infinity or plus infinity or both based on the type of the finite signal. So this is what I am trying to tell you. So finally I can say, suppose in the continuous time domain, let us take a certain finite amplitude signal and a finite duration. This present only for finite duration, then ROC will be entire explained, excluding either sigma is equal to -infinity or plus infinity or both based on the type of the finite signal. So this point always you have to keep in your mind. So let's go for the another point, which is a discrete time signal with finite amplitude and finite duration. The ROC will be entire jet plane, but excluding point circle or infinity circle or both based on the type of the finite signal present. So listen carefully. Same concept we are going to apply for even discrete time domain also. So I already told you, when f of n is equal to 0 for n less than 0, this is called as a right-sided signal. So if f of n is equal to 0 for t for n greater than 0, it is called as a left-sided signal. If f of n is not equal to 0 for all t, then we say it is a both-sided signal. Suppose if you take another signal like this, so you can see this is a signal f of n. So this is f of n. So it has a finite amplitude and it is present only for finite amount of duration. So finite amount of duration only it is present. Then it will have the ROC for this will be present for entire jet plane, excluding either point circle or infinity circle or both based on the type of the finite signal present. So you can say the amount of jet is not equal to either point circle or infinity, or it is also not equal to either these things. So what I am trying to do is very simple. Listen carefully. Here, when sigma is equal to -infinity, then what is the value of jet? You know, r is nothing but e to the power of sigma. I have already told you, r is nothing but mod of jet. So when sigma is equal to -infinity, so e to the power of -infinity is equal to 0. Hence it is a point. It is a point circle. Point circle will have 0 radius. Suppose sigma is equal to plus infinity, then what will happen? E to the power of infinity is equal to infinity, which is an infinite circle. So these things always you have to keep in your mind. So therefore we can say that, listen carefully, in the continuous time domain, a continuous time signal with finite amplitude and finite duration an ROC will be entire explained, excluding the sigma is called minus infinity or sigma is called plus infinity or both based on the type of the finite signal. Suppose if you are taking a discrete time signal which is having a finite amplitude and finite duration, an ROC will be entire jet plane excluding the point circle or infinite circle or both based on the type of the finite signal present. So finally, I can give the conclusion regarding these two concepts. Listen carefully. Suppose there is a continuous type signal with the finite amplitude and finite duration, then ROC will be entire explained but excluding sigma is equal to minus infinity or plus infinity or both based on the type of the finite signal present. Similarly, a discrete time signal with the finite amplitude and finite duration, then ROC will be entire jet plane but excluding point circle or infinite circle or both based on the type of the finite signal present. See, I have told you one point, right? If a signal which is not right-sided signal, if a signal which is not left-sided signal, then by default it is a both-sided signal. It is wrong. Actually, the signal. So this is not a right-sided signal. This is not left-sided signal. This is not even both-sided signal. This is basically finite signal. So this is the conclusion I can say. Finally, I can say, see, this signal, if you take this signal, this is not a right-sided signal. This is not a left-sided signal. This is not even two-sided signal. So by default, we can say this is nothing but a finite signal. This is a finite signal. So I already told you for right-sided signal in the time domain, the ROC is outward. It is basically to the right side. And for left-sided signal, the ROC is left side. And for both-sided signal, it is having a rectangular strip. We have some rectangular strip. For this one, all z plane. It is all is plane, excluding sigma is equal to positive infinity, minus infinity, or both. I have already told this point. Excluding. All is plane excluding. Whereas here, for this signal, for right-sided signal here, outward of a circle. Here, left-sided signal is inward of a circle. The angular strip. Here it is an angular strip. For this one, we can say it is all jet plane, but not point circle, but infinite circle and both. So this is what we have to keep in your mind. So finally, I can say, so for a continuous time domain, for right-sided signal, the ROC is to the right side, and for left-sided signal, the ROC is toward left side, and for a two-sided signal, the ROC is a rectangular strip between two bonded poles. Whereas for a finite duration sequence and a finite amplitude signal, definitely the ROC is all over the S-plane, excluding either plus infinity or minus infinity or both. Similarly, in the discrete time domain, for right-sided signal, the ROC is outward of a circle, and for left-sided signal, the ROC is inward of a circle, and for the two-sided signal, the ROC is having an angular strip. And for finite amplitude finite duration signal, the ROC is all over the jet plane, excluding the point circle or infinite circle or both, based on the type of this finite duration signal. So these points always you have to keep in your mind. So now the next point is, if ROC is right-sided, then it means that signal is right signal. If the ROC is right-sided, then it means the signal is right-sided signal. F of t is equal to 0 for t less than 0. Same thing I will prove you, right? Suppose if the ROC is toward the right side, means the signal is right-sided signal. If the ROC is toward the left side, means by default we can say the given signal is left-sided signal. If the ROC is a rectangular strip, means we can say by default that the signal is said to be two-sided signal or both-sided signal. If the ROC is having all over the plane, excluding either plus infinity or minus infinity or both ways, by default we can say it's a finite duration signal. Similarly, in the case of the z domain also we can say, if the ROC is outward of a circle, means the given circle is a right-sided signal. If the ROC is inward of a circle, means we can say it is a left-sided signal. If the ROC is having angular strip, means we say it is a two-sided signal or both-sided signal. And if the ROC is all over the S-plane, excluding either point circle or infinite circle or both, then we can say it's a finite duration sequence. So if you, by seeing the signal also we can tell the ROC signature, by seeing the ROC signature also we can tell the type of the signal. So by seeing the signal nature also we can tell the ROC nature. By seeing ROC also we can tell the signal nature. So this is the beautiness of these two concepts. So these things always you have to keep in your mind. So now let's go for the another point, which is if the number of poles are n, the number of possible ROCs are n plus 1. So if the number of poles are n, the number of possible ROCs are n plus 1. Why it is like this? Let us see here. Suppose let me take a one pole. Suppose let me take a one pole. So let me take only one pole. For one pole, so let me draw on a plane. Let me take a one pole like this. So what are the possible ROCs that you can get? You can get only two ROCs, right? One is to the left side and the other to the right side. So with the help of one pole, we got how many ROCs? Two ROCs, we got two ROCs. Similarly with n pole, how many ROCs we can get? N plus 2, n plus 2. So therefore we can say simply we can say with the help of one pole, it is a n plus 1. So n plus 1. So n plus 1. So small correction here. Let me rub this part. So let me rub this part. N plus 1. So you can see with the help of one pole, we have got two ROCs. So either this is a one ROC and this is the other ROC. So with the help of one pole, we got two ROCs. With the help of n pole, we will get n plus 1 number of ROCs. Suppose if you take two poles, let me show in the figure. So let me show in the figure. Suppose let me take the two poles. So let me take the two poles. So this is one pole and this is the other pole. So how many ROCs are possible? Let me show with the figure. So you can see clearly here. Let me draw with the other pen. I think you are not able to see that. So this is a one possible ROC. This is one possible ROC. Then the other possible ROC is this is the other possible ROC. Another possible ROC. Then the final ROC is this is the one more ROC. So how many ROCs are possible? Only three. So this is the one. This is the one. This is the one. So total three ROCs are possible. So with the help of two pole, three ROCs are possible. So 2 plus 1 ROCs are possible. Similarly, with the n pole, how many ROCs are possible? N plus 1 number of ROCs are possible. So this is a shortcut to remember. With the help of one pole, we are going to have the two possible ROCs are possible. With the help of two poles, three ROCs are possible. So with the help of n poles, n plus 1 number of ROCs are possible. So this formula you have to keep in your mind. So with the help of n pole, n plus 1 number of possible ROCs means this number of signals you can get from this expression. The next thing is number of ILT expressions. Number of ILT expressions is equal to number of ILT inverse Laplace transform expressions. Number of inverse Laplace transform expressions are number of distinct real poles. Number of distinct real poles plus 1 in the S plane. So number of distinct real poles plus 1. Number of distinct real poles plus 1. Because we need the real poles, not the complex poles. Complex poles we don't need. We don't need the complex poles. We need only real poles because we are going to draw the ROCs only from the real poles, right? So we need only real poles, which is number of inverse Laplace transform expressions are number of distinct real poles plus 1 in the S plane. And the number of ROCs present is nothing but number of ILT, number of inverse Z transform we can define in the Z plane, So listen carefully. Let us go one after the other. So number of inverse Laplace transform expressions is nothing but number of inverse Laplace transform expressions is equal to number of distinct real poles plus 1 in the S domain. Number of inverse Laplace transform expressions is equal to number of distinct real poles plus 1 in the S domain. So in the S domain, this formula you have to remember. Number of inverse Laplace transform expressions is equal to number of distinct real poles plus 1. Number of distinct real poles plus 1. Always you have to see only the number of distinct real poles, not the complex poles. Only the real poles you have to consider. So number of inverse Laplace transform expressions is equal to number of distinct real poles plus 1 in the S domain. The next thing is number of ROCs present is equal to number of inverse Z transform we can define in the Z plane. So number of ROCs present is equal to number of inverse Z transforms we can define in the Z plane. And the number of ILT expressions and the number of ILT expressions and the number of ILT inverse Laplace transform expressions is equal to number of distinct real poles plus 1 plus number of distinct complex poles seeing sigma only. So I want you to remember only this one. This is the final expression I want to remember, but not this one. So not this one, because there is also one more thing here. So I want you to remember only this one. So this expression always you have to keep it only. These two expressions you have to keep in your mind. So if the number of poles are n, the number of possible ROCs are n plus 1. So number of inverse Laplace transform expressions are nothing but, which is equal to number of distinct real poles plus 1 plus number of distinct complex poles seeing sigma only. So this is a important point always you have to keep in your mind. I explained this concept in the class also, but I want you to remember only this point, which is number of inverse Laplace transform expressions are the number of distinct real poles plus 1 plus number of distinct complex poles seeing sigma only. So this is what I am trying to tell you. So you can see that number of inverse Laplace transform expressions are number of distinct real poles plus 1 plus number of distinct complex poles which are seeing sigma only. So number of inverse Laplace transform expressions is equal to number of distinct real poles plus 1 plus number of distinct complex poles seeing sigma only. So this point always you have to keep in your mind. So here in this one we are going to consider only the real poles, and here we are going to see only the complex poles. Both should have different sigma. Suppose let me give a small example. Suppose as my small example, suppose if the number of poles are like this, minus 2, plus 2, and we can say 1 plus or minus j. Suppose if you got like this, then tell me number of independent Laplace transform expressions. What is the first thing? Number of distinct real poles. Now see only the real poles. So see only the real poles. In this, how many distinct number of real poles are there? Only 1 plus 1. Only 2 are there. So 2 plus, now to add 1 plus number of distinct complex poles. So this is also complex pole, right? Only by seeing sigma, only sigma or consider only that is 1. So 2 plus 1 is nothing but 4. So this is the 4 number of inverse Laplace, we can say number of inverse Laplace transform expressions. Suppose another example. Suppose we have like this, minus 2, plus 2, and 2 plus or minus j. Suppose if you have like this, then what is the formula? Number of distinct real poles. Are only 2 plus 1 plus now number of distinct complex poles seeing sigma only. If you see sigma 2 which is already present here, so you don't have to consider. So it will become only 3. So in that case, so this is what I am trying to tell you. So this point always you have to keep in mind. So suppose if you forgot, you can draw the graph, right? If you draw the graph, you will get to know. Suppose for this one, if I draw the graph, how I am going to look like? So listen carefully. Here minus 2 2 times. Here plus 2 2 times. Here like this here. You will get here 1 plus or minus j. 1 plus j and 1 minus j. So I will take it like this. So now you can see how many ROCs are possible. You can see. So here 1 ROC, here 1 ROC, here 1 ROC, and here also 1 ROC. So total 1, 2, 3, 4. 4 also possible. Yes, 4 possible here. Same thing I will take. Suppose here, if you draw for this picture, then what I can say for this one? Here it is a minus 2 2 times. Here plus 2 2 times. 2 plus or minus j. So here also same 2 plus or j. So if you draw the lines, what you can get? Only 3 ROCs are possible. This is 1, and this is 1. With 3 ROCs are possible. Same thing I have told you, right? So even though if you forget the formula also, but if you draw the graph, if you draw this picture, from this we can say how many ROCs are possible. We can easily say just by drawing the picture. Even if you forgot the formula, just by drawing the picture, we can get the conclusion, we can get the concept, right? So that is what I am trying to tell you. So for a given, suppose for a given f of s, try to find all the poles. and draw the picture and draw the straight lines, and then from it we can figure out how many number of RS are possible. We can easily figure out. Because RS will never include the poles. So from that we can draw the picture. So always you have to draw a sigma. From sigma only you have to draw a straight line and you have to draw the ROC. So this is what you can see clearly here. So therefore, what is the formula you have to remember? Number of inverse Laplace transform is equal to number of distinct real poles plus 1 plus number of distinct complex poles, same sigma only. Even though you forgot this expression, by place of the graph, you can get back the formula. You can get back the expression. So even though you forgot this formula, still you can get that concept, right? So now, this one you don't have to remember, right? If you remember this one, you don't have to remember this one, because this is a suppose if the complex poles are not present, this is a formula you have to use. But if the complex poles are also present, then by default you have to use this one. So complex pole also you need to consider. You have to draw a straight line from that. But you need to check this complex pole sigma and this sigma are different. If they are same means this will be not at all useful. But if they are different means then you have to use this one. So this is what I am trying to tell you. The number of ROCs present is equal to number of inverse Z transform that we are going to define the same thing. See, number of, what is the meaning of this one? See, basically, for this one, for this ROC, you are going to get one inverse Laplace transform expression you are going to get. For this ROC, you are going to get one more Laplace transform expression. For this ROC, one more Laplace transform expression you are going to get. For this domain also, you are going to get one more inverse Laplace transform expressions. So for each and every ROC, we are going to get corresponding inverse Laplace transform expressions. So therefore, we can say that same thing, number of ROCs present is equal to number of inverse Z transform we can define, or also number of inverse Laplace transform also we can define. So number of ROCs is nothing but number of ILT or IZT expressions. So let me write here. So number of ROCs is equal to number of inverse Laplace transform expressions or number of inverse Z transform expressions. So this is what I am trying to tell you. So number of ROCs present is equal to number of inverse Z transform expressions or inverse Laplace transform expressions in the Z plane as well as in the S plane. So this is what you have to keep in your mind. And always you have to remember number of poles is equal to the number of possible ROCs are n plus 1. As you can see clearly from the term. Even though you forgot that, you can easily by graph also you can get this discussed, right? So therefore, I want you to remember only one thing. The number of ROCs is always equal to number of ROCs is nothing but for each and every ROC you are going to get the corresponding time domain, continuous time domain or the discrete time domain expression. So therefore, number of ROCs is equal to number of inverse Laplace transform expressions or number of inverse Z transform expressions. So here you can write even like this, which is equal to number of inverse Laplace transform expressions we can define in the S plane. So in the S plane. So these things always you have to keep in your mind. So even though you forgot them, still you can get them. So this is what I am trying to tell you. So I want to remember these things. Number of poles is equal to number of possible ROCs are n plus 1. And I have already told you number of ROCs is nothing but base point number of ILT expressions or base point number of inverse Z transform expressions that we are going to get defined. Even though you forgot this formula, with the help of this concept, you can define how many number of ROCs that are going to get. Number of ROCs are nothing but number of expressions. So number of ROCs are nothing but number of expressions. Either it is a inverse Laplace transform expression or inverse Laplace transform expressions or inverse Z transform expressions. So basically here, number of ILT expressions means this number of ROCs are possible. So for each and every ROC we are going to get corresponding ILT of IZT expression. So finally I can say that number of ROCs possible is equal to number of ILT expressions or number of inverse Z transform expressions. So just by seeing the graph, we can say what are the ROCs are possible, and by drawing the graph, we can tell where the ROCs are present, and where we can get the expressions, and we can easily get. So these things always you have to keep in your mind. Now we are going to discuss the another point, which is the important concept, the system response. So this is a very, very important concept. I request you to present this concept in a very detailed manner. So y of n is the y1 of n plus y2 of n. So y of n is a summation of the y1 of n and y2 of n. So y of n is called as the zero input response, and y2 of n is called as the zero state response. Listen carefully. Y1 of n is called as the zero input response, and y2 of n is called as a zero state response. So what's the meaning of zero input response? Here input is zero. So because of these non-zero state variables, we are going to get the output that is called as the zero input response. And this is called as the y2 of n is called zero state response. Zero state response means here the states are zero. The states are zero. Because of input, we are going to get the output. So because of this reason only, it is called as the zero state response. So y1 of n is nothing but this is the response due to the initial conditions. So y1 of n is nothing but this is basically, this response is basically due to the initial conditions, non-zero initial conditions or zero input response also you can say. And y2 of n is nothing but this is the response due to initially relaxed system, or we can say zero state response also we can say. So simply listen carefully. Here the output y of n is a summation of the two outputs, which is y1 of n and y2 of n. y1 of n is called as the zero input response. Zero input response means input is zero. So because of non-zero state variables, we are going to get the output. Similarly, y2 of n is called zero state response means the state variables are zero. So because of the input, non-zero input, we are going to get the output. So therefore, y1 of n is nothing but this is the response due to the initial state conditions, or we can say zero input response also we can say. And y2 of n is nothing but this is due to initially relaxed system, or also we can say zero state response. And y2 of n, this we can obtain by the convolution method. So y2 of n that we are going to basically get with the help of the convolution method. And y1 of n is also called as the natural response, or the zero input response, or the transient response also we can say. Whereas y2 of n, this is called as the forced response, or the zero state response, or the steady state response also we can say. So finally, let me give the clarity. So y of n is nothing but, let me give the clarity, y1 of n plus y2 of n. So this y of n is called as the zero input response, because here input is assumed, input is zero. Because of non-zero state variables, we are going to get the output. So because of this reason only, it is called as a zero input response. Whereas here this is called as a zero state response, means here input is not equal to zero, but the state variables are zero. So because of this, we are going to get the output that is called zero state response. So this is also called as the natural response, or complementary solution also we can say, or transient response also we can call this as like different names. Whereas this is called as the we can say forced response, or particular solution, or we can say that the steady state response. So these are the different names. So this y2 of n, we are going to get with the help of convolution also we can get this response. So basically, whatever the steady state response that we are going to get by different techniques. By using different techniques, we can get back the steady state response. So one of the method is convolution method also. With the help of this method also, we can get back this zero state response, or the steady state response. So finally, I can say only one thing. Y of n is a summation of the y1 of n and y2 of n, where y1 of n is called zero input response and this is called zero state response. So this zero input response is the input is zero. So because of non-zero state variables, we are going to get the output. So because of this reason, it is called as a zero input response. Whereas y2 of n is nothing but here input is not equal to zero, but because of zero state variables, here state variables are zero. But because of non-zero input, we are going to get the output. So because of this, it is called zero state response. So this is also called as a natural response, or transient response, or the complementary solution. Whereas this is called as the forced response, or the steady state response, or the particular solution. So I already told you there are different techniques now to get the steady state response, and one of the method is the convolution method. So these things always you have to keep in your mind. So now let's go for the another concept. This is a very, very important and beautiful concept. I request you to remember this concept in a very detailed manner. So now, listen carefully. Initial and final value theorem. So we are going to apply the initial value theorem and the final value theorem both in the Laplace transform domain as well as the Z transform domain. And these two things we are going to discuss in a very detailed manner. So listen carefully. So whenever you are going to apply the unilateral transform. Unilateral transform is, I've already told you, unilateral transform is we are doing the integration from t is equal to 0 to infinity only. So we are going to apply the unilateral Laplace transform. So for f of t, if you apply the unilateral Laplace transform, we are going to get f of s. So you know f of s is expression nothing but f of s is equal to integration from t is equal to 0 to infinity f of t into e to the power of minus st into dt. So this is the unilateral Laplace transform. So what is the initial value theorem? F of 0 is equal to limit s tends to infinity s into f of s. This is called as the initial value theorem. And final value theorem is f of infinity is equal to limit s tends to 0 s into f of s. So this is called as the final value theorem. Here f of s is nothing but it is in the rational, it is in the p by q format in the rational number form, which is numerator by denominator. So these things always you have to keep in mind. So initial value theorem is nothing but limit t tends to 0 f of t is equal to f of 0 is equal to limit s tends to infinity s into f of s. Here t is 0 means s is infinity. And final value theorem limit t tends to infinity f of t is equal to f of infinity is equal to limit s tends to 0 s into f of s. So I have already told you t is tending to 0 means s is into infinity. If t is tending to infinity means s tends to 0. So these things always you have to keep in mind. So f of s is basically in the format of the numerator by denominator. So if the numerator degree is lesser than the denominator degree, then only apply the initial value theorem, otherwise it is undefined. So if the numerator degree is lesser than the denominator degree, then only we have to apply the initial value theorem, otherwise it is undefined. So always you have to think here, before applying the initial value theorem, first you have to check that the numerator degree is lesser than the denominator degree, then only we have to apply the initial value theorem, otherwise we don't have to apply. The next point is, if the pole of the assembly f of s, if it is purely in LHS, then only apply the final value theorem, otherwise answer is indeterminate. If the pole of the assembly f of s is on the imaginary and LHS, then don't apply the fa of t, final value theorem. I already told you, listen carefully, these 2 points always you have to keep in your mind. So, whenever the numerator degree is lesser than the denominator degree, then only we have to apply the initial value theorem. Otherwise, we don't have to apply the initial value theorem, or simply we can say it is undefined. Suppose f of s is nothing but, suppose if the system is stable, stable means all the poles are going to lie in the rest of s plane, then only we have to apply the final value theorem. Final value theorem is applied only for a stable system. For an unstable system, there will be no final value because it always tends to infinity. So therefore, I want to remember only one thing, which is, so if you want to apply the initial theorem, the formula I have already told you, the condition is when the numerator degree is lesser than denominator degree, then only you have to apply the initial value theorem. Otherwise, it is undefined. But when you want to apply the final value theorem, the first thing that you need to check is whether the given system is stable or not. Stable means if all the poles of s and f of s, if they are going to lie in the LHS of s plane, then only you have to apply the final value theorem. Suppose if they are going to lie on the imaginary axis or on the RHS, by default we can say the given system is not the unstable system or the unstable system. So for these two systems, definitely there is the response will always increasing in nature. So or it is oscillating in nature. So there will be no steady state value. So because of that reason only, we can say don't apply when the s and f of s as the roots on the imaginary axis or in the axis of the s plane. So finally, I can say I've already told you the formulas of the initial value and the final value. But if before you apply, you need to check these conditions whether these are satisfying or not. Which is when the numerator degree is less than denominator degree, then only you have to apply the initial value theorem. Otherwise, don't apply. So otherwise, this is undefined. Suppose if the poles of the s and f of s, if they are going to lie purely in LHS, then only you have to apply the final value theorem because the system is said to be stable. Suppose if the poles are going to lie, if the poles of s and f of s, if they are going to lie on the imaginary axis or on the LHS, then the given system is said to be imaginary stable system or the unstable system. So because of this, what is going to happen? The response is always oscillating in nature or increasing in nature. So there will be no steady state value. So we can say now then in that case don't apply this final value theorem because it is the answer is indeterminate. We cannot figure it out because we cannot figure it out. So this is what I am trying to tell you. So when the numerator degree is lesser than denominator degree, then only you have to apply the initial value theorem. Otherwise, it is undefined. If the poles of the s and f of s, if they are going to purely lie in the rest of s plane, then only you have to apply the final value theorem. Suppose if the poles of the s and f of s, if they are going to lie on the imaginary axis or on the RHS of s plane, then the response is oscillatory or increasing in nature. So because of this, there will be no final value. There will be no steady state value. So because of this reason, don't apply in this case for marginal stable system and the unstable system. Then don't apply the final value theorem. Simply we can say this is an indeterminate form. Indeterminate form we can easily say. So now the same concept now we are going to apply for the unilateral jet transform. Unilateral jet transform. Here you should write U jet T, not ULT. So U jet T, unilateral jet transform. So a small correction here, likely this is not ULT, this is U jet T because unilateral jet transform we are going to apply. So what is the formula? For f of n, if you are going to apply the unilateral jet transform, what is the formula? Sigma n is equal to 0 to infinity f of n into e to the power of minus n. Then what is the formula you have to remember? You have to remember these formulas. This formula is very, very important. So here these formulas you have to remember. So in the case of S domain and in the case of Z domain, the f of 0 is equal to limit s tends to infinity s into f of s. The f of infinity is equal to limit s tends to 0 s into f of s. Similarly in the case of Z domain. So listen carefully. Here f of 0 is equal to limit. Here z is same, z is tends to infinity. Here 1 minus z to the power of minus 1 into f of z. So if you simplify, z to the power of minus 1 nothing but 1 by j. So in place of z, if you substitute infinity, 1 with z is nothing but 0. So 1 minus 0 into f is nothing but f of z. So you can even write like that also. So if you simplify, it will become limit z tends to infinity f of z. Similarly, f of infinity if you want, then its value is equal to limit z tends to 1. Z tends to 1. Z tends to 1. 1 minus z to the power of minus 1 into f of s, f of z. So this part always you have to keep in mind. Suppose if you simplify, what you are going to get? So if you simplify, 1 minus 1 by z is z minus 1 by z. In place of z, if you substitute 1, then what are you going to get in the denominator? If you substitute, then limit z tends to 1, z minus 1, then z is nothing but 1 into f of z. You can write like this also, you can write. So these are different ways of writing. So this you have to remember. See, I already told you, here z is nothing but e to the power of s, I already told you. Suppose if s tends to infinity, then z is also tends to infinity. Suppose if s tends to 0, then z tends to 1. Z tends to 1, right? So with the help of this relation, that is called e to the power of s. So therefore, you can see the formula is same. The nature of the formula is same. In place of s, what I written? 1 minus e to the power of minus 1. So this you have to remember, right? This is in the s domain and this is in the z domain. So this you don't, if this you think you are easily remember. So if you know this one, how to get this one, I will tell you. So here z is nothing but e to the power of s. So here s is tending to infinity. So as s tends to infinity, z is also tends to infinity. So let me tends to infinity. F of s means f of z. In place of this, write 1 minus e to the power of minus 1. That's it. So if you simplify, what we are going to get? In place of z, I have substitute 1, then we are going to get simply. Then if you substitute, in place of z, if you substitute infinity, then we are going to get f of z. If you simplify, we are going to get f of z. Similarly, here limit is tends to 0. In place of this, if you substitute 0, we are going to z is equal to 1. So limit z tends to 1. Then s is nothing but 1 minus z to the power of minus 1 into f of z. In place of, if you simplify, what you are going to get? Z minus 1 by z. In place of z, I substitute 1, then we are going to get z minus 1 into f of z. So these are the different ways of writing. So these two things always you have to keep in your mind. So the only thing is, I have replaced s by 1 minus z to the power of minus 1. So this point always you have to keep in your mind. So this is what I have replaced s by 1 minus z to the power of minus 1. So this is a point always you have to keep in your mind. So in place of s, I have substitute 1 minus z to the power of minus 1. So if you remember this one, everything is very simple. So this is the initial theorem and this is the final value theorem, as you can see clearly from this one. So if you remember the basic concept, getting this is a very simple piece of cake, right? So now, then what I have to do next here? So the next point is here. In the final value theorem, if the 1 minus z to the power of minus 1 into f of z or z minus 1 into f of z, the amount of the poles must lie inside the unit circle. Then only apply the final value theorem. then only apply the final value theorem. If they lie on the unit circle or outside the unit circle, the final value may be undefined, not equal to 0 or undetermined. It may be equal to infinity. So in jet transform, there is no condition for the application of the initial value theorem in a jet transform. So the initial value theorem, there is no condition. Directly you can apply. So there is no condition for this one. You can apply directly. You don't need to check anything. Just directly apply this one. But while applying this one, you have to have a condition. So there is a condition there. So what is the condition here? So therefore we can say, whenever you are going to apply the initial value theorem, there is no need of any checking any condition. Directly apply the formula. But if you want to check the final value theorem, which is if the 1 minus z to the power of minus 7 type of z or z plus 7 type of z, if the magnitude of the poles, they must lie inside the unit circle. They must lie only in the inside unit circle. Why it is like this? Suppose if they are going to lie inside the unit circle and if the ROC is outward, definitely, suppose, see, listen carefully, if they are going to lie inside the unit circle, then what is going to happen? If they are going to lie inside the unit circle, means definitely we can say in the S plane, all the roots are going to lie only on the LS of S plane. So because of that, what is going to happen? The system is said to be stable. Then only you can apply the final value theorem. Suppose if they are going to lie on the unit circle or on the unit circle, or if they are going to lie on the unit circle or outside the unit circle, then the final value theorem will not applicable. It may be undetermined or undefined. So what I am trying to tell you is very simple. That see, in the case of jet transform, you don't have to, if there is no condition while applying the initial value theorem, but while applying the final value theorem, there is a condition, which is if the 1 minute z to the power of plus 1 type of z or z minus 1 type of z, first you have to check the poles. If this matter of the poles, they must lie only inside the unit circle, then only you have to apply the final value theorem. Suppose if this matter of the poles, if they are going to lie on the unit circle or on the outside of the unit circle, then you don't have to apply the final value theorem. Why it is like this? Because if the matter of the poles, if they are going to lie inside the unit circle, means we can say in the S domain, all the roots are going to lie in the LHS of S plane. So because of this, what is going to happen? The system is said to be stable. But if the roots are going to lie on the imaginary axis, means the roots are going to lie on the unit circle. Suppose if the roots are going to lie in the arcs of S plane, means they are going to lie outside the unit circle. So in both these cases, the system must be stable or unstable system. So because of this, the response will be always oscillatory in nature, always increasing with respect to time. So because of this, there is no steady state value or there is no final value. So because of this, it is undefined or not defined in nature. So in the jet transform, there is no condition for the application of the initial value theorem in the jet transform. So in jet transform, there is no condition for the application of the initial value theorem in the jet transform. So finally, I can say, listen carefully, whenever in the unilateral Laplace transform, the initial value theorem is f of 0 is equal to s to infinity s into f of s, and f of infinity is equal to s to 0 s into f of s. So if you see clearly, while applying the initial value theorem, first you have to check whether the numerical degree is lesser than the d of the degree of length. Then only you have to apply the initial value theorem. Otherwise, it is undefined. While applying the final value theorem, see, final value theorem is the answer should be very constant value you should get. If you're not getting this, the responses are oscillating or increasing in nature. So first you have to check the roots of the s into f of s. If the roots are going to lie in the purely of s plane, the system is stable, so it will have some finite value. So therefore, you are going to get some finite value. Suppose if the roots are going to lie on the imaginary axis or on the RS of s plane, then the responses are purely oscillatory in nature or increasing in nature. So because of this, there is no final steady state value. So therefore, we can say it is undefined. Suppose in the jet transform, I have already told you the only thing is replace s by 1 minus to the power of minus 1, and you know z is equal to the power of s. If s tends to infinity, z tends to infinity. If s tends to 0, z tends to 1. So limit s tends to infinity means z tends to infinity. Here s tends to 0 means z tends to 1. Then everything is same. In place of s, I have substitute 1 minus to the power of minus 1 into f of z. If you simplify, we are going to get this is f of z, and if you simplify this, we are going to get z minus 1 into f of z. So while applying the initial value theorem, there is no condition. Direct apply in the jet transform. But while applying this one, final value theorem, first thing is you have to check the for z minus 1 type of z, try to check the amount of the poles. If they are going to lie in the purely inside the unit circle, then only you have to apply this formula. Otherwise, if they are going to lie on the imaginary axis or if they are going to lie on the unit circle or also the unit circle, then the system is Marsden stable system or the unstable or the unstable system. So because of this, there is no finite value. So in that case, we can say this undefined. This undefined, we can say in that case. So this is what you have to keep in your mind. So let me give you one concept so that you can easily able to understand mapping. So this concept I have not written, but let me give you the concept of mapping. So this concept is very, very important. So this is the S domain and this is the Z domain. So this is a S domain and this is a Z domain. So this concept of mapping is very, very important. So let me tell you in a very detailed manner. So let me tell you in a very detailed manner. The concept is the regarding the mapping. So mapping concept I am going to tell you. So this is the S plane and this is the Z plane. Z plane. So mapping I am going to tell you Z plane and S plane. I am going to tell you the mapping. So now this is nothing but sigma. This is the J omega. So S is nothing but sigma plus J omega. So you know what is the concept? You know Z is nothing but Z is equal to e to the power of S. You know S is equal to sigma plus J omega. So to simplify, e to the power of sigma into e to the power of J omega. So e to the power of sigma I am going to assume which is R and this is e to the power of J omega. So what is magnitude of Z? Magnitude of Z is equal to R. R is equal to e to the power of sigma. So now you see, suppose I can write like this, right? So Z is equal to the power of sigma and e to the power of J omega I can write. Suppose all these points, suppose I want to map where it will go in the Z plane that I want to see. So all these points are nothing but sigma. Sigma is lesser than 0. So if the points which are going to line the HS planes, sigma is less than 0, so I want to basically map all these points, edges of the S plane and the Z plane I want to map. So what it will get? So you can see, what is the first case? Sigma is lesser than 0. If sigma is lesser than 0, then what is going to happen? Let us see. So Z is equal to e to the power of sigma into e to the power of J omega. If sigma is lesser than 0, then what is going to happen to the e to the power of sigma? So let us assume sigma is equal to -1. Then e to the power of -1 nothing but 1 by e. 1 by is nothing but it is lesser than 1. 1 by is nothing but it is lesser than 1 because u is greater than u 10. So the ratio is lesser than 1. Therefore we can say it is lesser than 1. So we can say the amount of Z is lesser than 1. It is lesser than 1. It is lesser than 1 means we can say it is going to lie inside the unit circle. So if you write in the polar format, then what you are going to get? R is equal to e to the power of sigma at an angle of omega. Omega can be anything. So all these points are going to lie inside the unit circle. So all are going to lie inside the unit circle. So let us take this is a unit circle. So this is a unit circle. So all are going to lie inside the unit circle, right? What is the second case? So what is the first case? All the LHS of the S plane, they are going to purely lie inside the unit circle. I want to tell you, all these points are going to map inside the unit circle. Suppose the second case is, now I will take only the imaginary axis. Imaginary axis means I want to map all the points present on the imaginary axis. I want to map from S plane to Z plane. So where they are going to get matched, let us see. In that case, sigma is equal to 0. So you know Z is equal to e to the power of sigma into e to the power of J omega. So e to the power of sigma is nothing but e to the power of J is nothing but 1 into e to the power of J omega. So if you write in polar format 1 into an angle of omega. So therefore all these points on the imaginary axis, they are going to map on the unit circle. Similarly, what is the third case? For the points which are going to lie in the arches of S plane. Arches of S plane means sigma is greater than 0. Then what is going to happen? Z is nothing but e to the power of sigma into e to the power of J omega. Sigma is greater than 0. Means let us say sigma is equal to, so A square is nothing but greater than 1. So therefore we can say e to the power of sigma at an angle of omega. So this radius is greater than 1. Radius is greater than 1 means it is outside the unit circle. So it is outside the unit circle means where they are going to get mapped. So finally what I can say? I can say only one important point, which is the LHS of the S plane, all the points in the LHS of S plane, they are going to map inside the unit circle, and all the points on the imaginary axis, they are going to map on the unit circle, and all the points of the RS of the S plane, they are going to map outside the unit circle. So this is what I am trying to tell you. So finally I can say all the points in the ellipse of the S-plane, they are going to map inside the unit circle, and all the points on the imaginary axis, they are going to map on the unit circle, and all the points of the also of S-plane, they are going to map outside the unit circle. So based on the formula, that is equal to e to the power of S is equal to sigma plus j omega. So e to the power of sigma into e to the power of j omega. When sigma is less than 0, then the radius is less than 1. If sigma is equal to 0, the radius is equal to 1. And sigma is greater than 1, the radius is greater than 1. That's it. So therefore we can say that all the points of the ellipse of S-plane, they are going to map inside the unit circle, and all the points on the imaginary axis of S-plane, they are going to map on the unit circle, and all the points on the axis of S-plane, they are going to map outside the unit circle. So this is a point always you have to keep in your mind. So even though if you forget this one, but if you know this concept, it is called e to the power of S. From this concept, we can go for the mapping concept. So finally, all the points of the ellipse of S-plane, they are going to map inside the unit circle, and all the points on the imaginary axis of the S-plane, they are going to map on the unit circle, and all the points on the also of the S-plane, they are going to map on the output of the unit circle. So that is equal to e to the power of S is equal to sigma plus j omega. So if we simplify, we are going to e to the power of sigma into e to the power of j omega. So R at an angle of omega, we can write like this: R at an angle of omega. So R at an angle of omega. If sigma is less than 0 means R is less than 1. If sigma is equal to 0 means R is equal to 1. If sigma is greater than 0 means R is greater than 1. So this is what we can say. If sigma is less than 0 means R is less than 1. If sigma is equal to 0 means R is equal to 1. If sigma is greater than 0 means R is greater than 1. So this is a thing. Finally, I can say that all the points of the ellipse of S-plane, they are going to map inside the unit circle, and all the points on the imaginary axis, they are going to map on the unit circle, and all the points of the ellipse of S-plane, they are going to map outside the unit circle. So this is the mapping concept you have to keep in your mind. So a system is said to be stable when all the points are going to lie in the ellipse of S-plane. So if you map, here we are going to get inside the unit circle. So therefore we can say, so there is a reason if all the roots are going to lie inside the unit circle, means all the roots are going to lie in the ellipse of the S-plane, then we can say the given system is stable. The given system is said to be stable in that case. Then only you are going to get a finite value. Suppose if the roots are going to lie on the imaginary axis, and the roots are going to lie on the axis of S-plane, then definitely what we can say, the roots are going to lie on the unit circle or outside the unit circle. In that case, the system is marginally stable system or unstable system. Should there be the response is always oscillating in nature or increasing in nature. Should there be no finite value, because it will never have a finite value. So because of this, there is in that case we can say it is undefined. So this is the concept I am trying to tell you. So this mapping concept always you have to keep in your mind. Now we are going to discuss about the another new concept, which is the sampling theorem. So sampling theorem we are going to discuss in a very detailed manner. So what is the meaning of sampling theorem? Suppose if there is some original signal, so we are going to the sample of the signal, and then we are going to transmit the signal, and finally with the help of resampling we can get back the original signal. That is the basic concept of the sampling. So now we'll discuss the some more detail regarding the sampling theorem. If you sample the original signal at higher TS, if you sample the original signal at higher TS, the reconstructed signal from samples is no more original signal. So if you sample the original signal at higher TS, the reconstructed signal from the samples is no more original signal. So what is the meaning of this one? Suppose if you are going to sample the original signal at higher than TS, TS is the sampling time period, then the reconstructed signal from samples is no more original signal. So what is the meaning of this one? Let me tell you. See, suppose if time period T is less than or equal to TS, see, whenever you are going to sample with less than or equal to sampling time period, then whatever the reconstructed signal is nothing but it is the reconstructed signal is equal to original signal. So RES we call as a reconstructed signal is equal to original signal. Suppose T is greater than TS, then the reconstructed signal from the samples is no more original signal. So therefore you can see clearly, suppose if you are sampling the original signal at a lesser than or equal to sampling time period, then the reconstructed signal from the samples is always a original signal. But if you are going to sample the original signal at higher than Ts, the reconsidered signal from the samples is no more the original signal. So now, as you can see clearly from this picture, so we can say that if you are going to sample the original signal at a time period which is less than or equal to sampling time period, then whatever the reconsidered signal is always equal to the original signal. Suppose if you are going to sample the original signal at a higher than sampling time period, then the reconsidered signal from the samples is no more original signal. So finally, I can say that if you are going to sample the original signal at less than or equal to sampling time period, then the reconsidered signal from the samples is always a original signal. Suppose if you are going to sample the original signal at a higher than sampling time period, then the reconsidered signal from the samples is no more original signal. So these points always you have to keep in your mind. So now let's go for the other point. So don't choose whatever TS you want. There are some guidelines. If you follow, then the reconsidered signal will be similar to the original signal. Same thing. So don't choose whatever TS you want. There are some guidelines. If you follow, then the reconsidered signal will be similar to original signal. Say what I told you. See always it is not, see whatever the sampling period you want, that you can't take. There are some constraints, there are some conditions, there are some guidelines you have to follow, and you have to use only those sampling time period in order to reconstruct the original signal from the samples. So don't choose whatever TS you want. There are some guidelines. If you follow, then the reconsidered signal will be similar to the original signal. So in simple words, I can say like this. Suppose here, don't choose whatever TS you want. There are some guidelines. If you follow, then the reconsidered signal will be similar to the original signal. So finally, I can say only one important point, which is, see, I have already told you there are conditions while choosing the sampling time period, the sampling frequency. So then only we can get back the original signal from the reconstructed signal. So this is a point always you have to keep in mind. So there are some conditions or there are some constraints on the sampling. So you have to follow only those things in order to get back the original signal from the reconstructed signal. So don't choose whatever TS you want. There are some guidelines. If you follow, then the reconstructed signal will be similar to the original signal. So this point always you have to keep in your mind. So finally, I can say only one important thing, which is simply I can say like this. Don't choose whatever TS you want. There are some guidelines. If you follow, then the reconsidered signal will be similar to the original signal. So finally, I can say, if you are going to sample the original signal at a less than or equal to sampling time period, then the reconsidered signal is equal to original signal. But if you are going to sample the original signal at higher than TS, then the reconsidered signal is no more original signal. So basically, you can't choose whatever the TS you want. There are some guidelines you need to follow in order to, and then only you have to follow, then only the reconsidered signal will be similar to the original signal. Then what is TS? TS is called as a sampling interval. TS is called as a sampling interval or sampling time period also you can say anything. Sampling time period or sampling interval also you can say. The Fs is the sampling frequency which is equal to 1 by Ts. Sampling frequency. Suppose if you want in terms of omega naught, sometimes they use omega naught or omega s also they will use. It is up to you. It is just a small notation, right? So either you can use omega s or either you can use omega naught. It is not at all a big issue. So omega naught or omega s is equal to 2 pi Fs. Fs means these many samples are sampled in 1 second. So what's the meaning of Fs? These many samples are sampled in 1 second. So these many number of samples are sampled in 1 second from the original signal. So Fs is nothing but these many samples are sampled in 1 second from the original signal. So this is a point always you have to keep in your mind. So now f of t is a continuous time signal, but we are going to sample it, right? So we are going to sample it. So as we are going to get sample the signal, so we are going to write in a discrete time domain, because for a continuous time signal, if we are going to sample with the delta, then the resultant signal will be in the discrete nature. Then we can write f of nts. F of nts we can write. So this is f of nts, where t is nothing but nts, because I've already told you whatever this continuous time domain signal that we have sampled with the help of that sample signals, we can say that impulse signals, then we are going to get the discrete time domain signal that we are going to get. So f of t will become f of nts, where n is the integer value and ts is the sampling interval. So we have to replace t by nts because the time domain signal has converted to discrete time signal because of the sampling, So these things always you have to keep in your mind.